how API works. The main question comes is like when you hit www.youtube.com, how does the request reach to YouTube server? Now a question may appear like, what is IP address and how can we see that? Let me show that to you. So in your computer you can simply open the command prompt. Okay, here we open the command. Now let's go through some of the doubts. So the first question is like, there only one DNS? How request is routed to the nearest DNS? Who pays for DNS? What you can do is like right click on the browser, you can click on the inspect part, then the network layer. Okay, so say for example I go to images, right? So you can see multiple API calls and all. What is the difference between the gateway and the load balancer? Like what is a firewall? Like is it a server or what kind of thing is it? What is the difference between L3 gateway versus L7 gateway? Similarly L4 load balancer versus L7 load balancer. How does the L7 gateway redirect or route the request to the correct microservice? Alright, so I'll come to our diagram actually, which we started for client and servers, and I'll show you all the components mentioned here. This video can help you getting your dream company offer letter. How? Let me tell you. So my friend was asked this question in the interview: how API works. Looks simple, right? But here's the trick part. This was the only question in the interview. Now it seems tricky, right? Because you have to talk about it for 40 to 45 minutes. There is no other question. So this was the only question that was asked in the system design interview round, which means the interviewer is going to grill or test your deep system design fundamental knowledge. You can't just say here, okay, there is one client and there is one server and API is like request from the client and response from the server. Okay, it's like you will say this like 2-3 minutes or like max you will explain the basic flow. But what about the other questions which will come? Do you have the complete fundamental understanding of how API works? So in this video I'm going to talk in complete detail like what are the basic components and how the complete flow looks like, and we will go to the complete detailed information of each of the component. So make sure you watch this video till the end because it will clear your a lot of system design fundamentals. And once your fundamentals of system design are strong, you will appear in the interviews with great confidence and you can answer a lot of questions, right? So you never know, because of this video you can get your dream company offer letter, right? And the other part is, you see the content is free and I'm putting a lot of energy and effort in. What I want from you is to make sure you subscribe to the channel and share it with your friends so that all of us can learn and grow together. Alright, let's start how API works. So in this video I will talk a lot of basic stuff as well, but I will also go to very detailed and advanced level. So in case some of the things in the beginning you find you know about it, don't worry, just keep on watching because you will find a lot of stuff in this video which you will learn for the first time, right? Okay, so let's first start with what is an API. So the full form of API is application programming interface. API is a contract through which client and server interact. Now the API can be of various types like REST APIs, there are GraphQL as well, then gRPC, so etc. But we will mostly focus on the REST API in this video because REST API is the most famous one. And once you get the understanding how the system works, it is quite similar for the remaining ones as well. So now what I will do is like I'll share with you all the components that will be involved in an API. Then we will talk about each of the component in detail. So let's start with a very basic and top level view. Okay, so first we have a client. Okay, what client means is like the end user, like you are watching this video, you might be watching this on your mobile phone. So in your mobile phone, whether it's like Android or iPhone, in that there is an application which is the YouTube app. So whenever you open the YouTube app, an API request is sent via your mobile phone application. How that happens? That happens by the application logic. The front-end developer has written that code. So whenever the application opens, there is a code written that from there an API request will be sent. Okay, now API request will be sent from the client to the server. So here I am drawing a server. Let me write server here. Okay, so this is the server. So now client, as I said, you can imagine it can be a mobile phone on which you are using the application. It can also be your desktop, right? On the browser you entered the link www.youtube.com and then it opened YouTube, right? Even that is acting as a client. So client can be your mobile phone application or your desktop browser. So the end user is interacting through a phone or a laptop or desktop, so that acts as a client. Okay, now to imagine client is very easy. You will say mobile phone or your desktop, but what about the server, right? So server, you can also imagine it's kind of a computer on which your code is written. Okay, but in the distributed system, it's not just one computer, there are multiple machines which can perform a lot of tasks. But on very small scale, if you want to understand, it's simply a computer on which there is some code written that will be called when an API request is received. Okay, so for example, you have written a function which will generate an image or anything like that. It can have any logic, so that is part of the server. Okay, now one question may appear is like, why API is actually required? Like, why can't client handle everything? It's very simple. You can say like, you have the YouTube application on your mobile phone. The front-end developers generally build like the UI stuff. You can say the buttons or some other stuff to which the user can interact to. Okay, but the application or this browser cannot have the complete data. You can imagine on YouTube, you can see the content of a lot of content creators, right? You can search for any kind of data there, any videos or all that stuff. So that can't be present in the application itself or in the browser itself. So you need data, right? When you open YouTube, it has two things. One is the things that you just see, like the buttons and the stuff that you can create on the application or on the website. But you also need the data, right? The video, for example, you're watching this video, you need that information or data that you get from the server. Okay, so that's why client will interact with the server. How do they interact? They interact using API. So I'm going from very basic level and I will just keep on increasing the bar here. This is going to be a very detailed video, don't worry about that. So basically, to get the data or store some data, anything like that, it will use the API to reach out to the server. Okay, and after that, as I said, on the very basic level, you can understand when you receive a request, that is a API on your server, which means you can imagine it like as a computer out there on which you have written some method or code, and then that code will be executed and you will create some output, right, that you want to return to the client. Okay, so you can imagine on the server side, we did some processing, gathered some data or whatever, and then we send it back to the client via what? API. Okay, so on technical note, from client, when you are giving input to the server for interaction, like for example, you want some data or you want to store some data, whatever, that is called as request. Okay, so client is requesting, like in normal English also you will understand in a very basic way. Okay, request, you are making a request, right? So client is making a request in the API to the server. Okay, and server is giving the output, right? So that output in technical terms is called as response. So the server is giving back the response. Client is making a request, server is giving back the response. So in normal English terms also, it looks very easy to remember, right? So these are the technical terms in API: request, response, client, server, right? On very basic level. Now to scale it a bit more, as we said, like server will handle a lot of data related work, right? It can save the data, it can fetch the data. So in generic terms, you have also one more layer, which is the database layer. So let me create here one more thing. I'll name it as database. Okay, so you have the database. What's the responsibility of database? So basically, the database will be used for data, as the name suggests. Okay, it will contain a lot of data. You can write data to it, update data to it, or you can delete data, or you can also read some data from the database. So these operations are called as the CRUD operations. So what does CRUD stand for? Like create, read, update, delete. So these major operations are performed on the database because it contains the data. You can create more data, you can read the data, whatever existing data is present, you can read that, then you can update some of the data, or you can also delete some of the data. Okay, So this is a very basic overview, like how things work, right? And maybe most of you already know this flow. Okay, so this part basically request and response. This is basically API, right? So I can write it here. You already may know this. There is client, there is server, there is database, then there is API. So in API, when client is asking something from the server, it's called request, and when server gives back the output, it's called the response. Okay, very basic overview, right? So let's move forward with it because we want to get more details in it. So our major flow in our question is related to this side, you can say, like we simply said from client a request will go to the server and server will give back the response, right? But what actually happens in between, like how does this all happen? So before going to that part, generally, like if you want to know the request and response in what format it is, so most of the times it is in JSON format. So JSON is used in most of the APIs, you would see that's very famous. There are other options as well to send like the request response format, but JSON is mostly used. So just to showcase you the request response, it would be something like this. So here you can see it's a get API method, and then this is basically the URL, and we are using HTTP 1.1 here. Don't worry about all this, I will cover all this information in detail in this video. Then this is the host, api.example.com. you can imagine it something like www.google.com or youtube.com, facebook.com, everything, all such things are host. So here the host is api.example.com. Then there is authorization, content type, accept, user agent. User agent will basically mean from where you are hitting this API. So for example, I ran this from Postman, so it says Postman, and here you can see it says JSON. So JSON, as I mentioned you, it's like a very famous way in which you send the request and the response. Okay, and rest of the stuff, don't worry, we will discuss about each of these things, but basically it's like host and URL will give you like where are you trying to hit the API. HTTP is the protocol. Get is a method. There are other methods as well like post, put, patch, delete, which can be used for API. And then authorization, it's basically to authorize the end user, like who is making the API call. To authenticate that user, we use the authorization, which is part of the headers. We'll talk about it later, don't worry. So this was an example of what client will send to the server, that is the request. Now let me also show you an example of the response, that is what server will send back to the client. Okay, so this is the example of the response. Okay, so first thing is it tells about the protocol, same as like HTTP 1.1. Then 200 is the status code, which basically tells you it was a successful API call, that whatever request was sent, it was successfully returned as a response. So whatever request was made, successful response has been sent from the server side. Okay, again there is content type, which is JSON. Cache control is there, which talks about no cache or cache. You can ignore it for now. Then basically you can see this is the response that is received. It provides a lot of information in it, and basically this format is in JSON. Okay, so this is the like just an example of how a request and response looks like. Okay, so let me remove all this and then we can go further in detail about all the components that will be required in the API. So what we are going to talk about is, first is the network layer. Okay, so network layer will contain the components like first is DNS, then there is TCP protocol, then there is TLS protocol that you should be aware about. I will talk about each of these in detail, but this is something that we are going to cover about and you should know about all of these fundamentals. So after that we are going to talk about the firewall, and after that there will be gateway and then load balancer. So we are going to talk about all of these things in this video in very detail, like how each of these work and how the complete flow will look like. Okay, so we will start with basically DNS. Now to understand this, let's see an example. Okay, so here is my channel on YouTube, Mohit Chhabra Tech. But if you see this URL out there, you will see it says https www.youtube.com/@Mohit Chhabra Tech, right? So let me just copy this and paste it here so that we can discuss about it. Okay, so this is the complete URL. Now if I can separate it out, now https is the protocol here, this part here is the host. So let me write it down here, host, and this part would be the URL part. Okay, so protocol, host, and URL, right? So now the main question comes is like, when you hit www.youtube.com, how does the request reach to YouTube server, right? Like, how are things working? This can't be just a magic thing happening automatically. How is this working? So this happens using one of the components named as DNS. Okay, so whenever from client, when we hit API request, it first reaches out to DNS. Okay, so let me write it down. This was our client and this is the DNS. Now you may ask like, why DNS is required, right? So let me explain it to you in a very simple way. Okay, so this is, say for example, your mobile phone. Okay, and in your mobile phone there is an application named as the contacts app. Okay, right? So you may have your friend, say for example John, right? And you want to call John. So what you generally do is, you're in your mobile phone, you simply click on the contacts app, you simply write John and click on the call button and it makes a call to John, right? Now let's understand like, how is this connection being made, right? Like, how does the phone know how to contact John? It's very simple. The phone numbers, it's very simple. It happens using the phone numbers. Say there is a number 9622718, whatever is the number. Okay, so this number is linked with John. So what you have done is, in your contacts application, you saved this number to John. Now whenever you are saying call John, it is simply making a call to this particular number, right? And why do we save the names? Because as a human, it's very easy for you to remember the names. It's difficult to remember the complete phone number. Say 10-digit phone number, it's difficult to remember. Most of us don't even remember more than 5 or 6 mobile phone numbers. Only the most nearby people, like your family or very close friends, you just remember those numbers. Apart from that, you just contact everyone using this contacts application, where you have this contact name. You simply click on the call on that contact name and the call happens, right? So as a human mindset, it's difficult to remember all such numbers. It's easier to remember the name. So you have linked name with phone number. Like, who is doing that? The contacts application is doing that for you, right? In similar way, internet understands IP address. Okay, like to making a phone call, you need a phone number. Similarly, internet needs a IP address, right? Now IP address may look something like this: 205.100.53.86. This is just one of the examples of random. I am saying the IP address, which is a valid IP address. Now you can simply see it's so difficult to remember all the IP address, right? It's even more difficult than remembering the phone number. So how would you remember all such things? Imagine you are just inputting 205.100.53.86 on your web browser. No, it doesn't looks feasible. So what we are good at is remembering the names. So we just know www.youtube.com. Now because the internet understands IP address, we need something or someone to convert or have this mapping between the name and the IP address. Who is doing that? DNS. So DNS is acting like the phone book of the internet. So whenever you write www.youtube.com, the DNS comes into picture. It basically converts that name to the IP address, and then the request is sent to that particular IP address. Okay, now a question may appear like, what is IP address and how can we see that? Let me show that to you. So in your computer, you can simply open the command prompt. Okay, here we open the command prompt and you simply type this ns lookup space www.google.com. okay, and you can see it will provide you the IP address. So this is the IP address. So let me show this to you. I go to the browser. In the browser I firstly write google.com. okay, so you know, like, it will open the Google. That's fine. Now this is very known thing, it will open Google. But now in the another tab, let's just paste this IP address. okay, 172.217.27.164. let's do it. In the new tab I'm doing this and paste. Okay, you can see it redirected to google.com. That means this is the IP address. So even if you put google.com or that IP address, it will redirect to the same website, because internally the internet understands the IP address only. So from that we get the understanding internet understands the IP address. okay, so and the DNS provides you the IP address mapped to the name. Now let's go to a deep version to it. Like we just said, it contains the mapping and it will provide you the IP address. But now the question comes, how will it provide you the IP address? Right? So let's try to understand that part. For example, user has hit this API. Okay. So first the DNS needs to resolve this host, right? It needs to provide you the IP address of this host. It does not care about the URL part, like whatever is present after this slash, the query parameters or the path parameters. It doesn't care about that. Its main focus is to provide the IP address of this host, right? This is a protocol, host, and the URL. So it focuses on the host part. So it will try to provide you IP address of this host. Now let's see how it provides you that. Okay, so the first thing the DNS tries is the browser cache. Okay, so whatever browser that you are using, like Chrome, Firefox, or anything else, they maintain a DNS cache. So what that means is, like, say for example, you have already visited api.example.com recently, then it would be present in your browser cache, and that's the first step to check it in the browser cache. If it is present in the cache and it is still valid, when I say it is still valid, it means based on the time to live, because cache has time to live, that is the expiry. Say for example, you can say whatever things that you have cached, you can keep the time to live or the expiry of like 5 minutes. So within next 5 minutes, if you hit that URL again, you can find that simply from the cache. You don't need to perform all the procedure. You can simply pick from the cache. Why? Because it's very fast. You can get the things from the cache and you don't need to perform the complete logic that we are going to discuss further. You don't need to go to the next steps. You will simply pick it here and give the results back to the user. So what you will do in this case is simply pick the IP address directly from the browser cache. So it will save a lot of time. So for example, in this complete case, as I said, the focus will be always on the host part. So host part is api.example.com, and it will simply give you this IP address 203.0.113.25. like this is an example of IPv4 address. Okay, let me write it down. IPv4, which is a format you can have like x.x.x.x. okay, so this is the IPv4 format. You can see 3 dots are present, and the range of x is actually 0 to 255. okay, so anything between 0 to 255, that will be considered as valid. okay, for example, you can see here 203, which lies in 0 to 255, same as like 0, 113, 25. okay, so this is the IPv4 address format. okay, so the first step is to check in the browser cache. Say for example, I visited google.com recently, so that would be present in the browser cache. Now next time I open google.com again, the IP address will be simply picked from the browser cache. okay, now in case like it is not present in your browser cache, when can that happen? It can happen in multiple cases, like you are visiting a URL for the first time, or the TTL has expired, the time to live, or which means the cache has expired. So in that case, we go to the step number 2. So that is using the local cache or your operating system level cache. okay, this is the second step, just in case you are not able to find the IP address from the browser cache. okay, so we move to the second step, which is the OS resolver or the local cache. So what happens is, like your operating system like Windows or Linux, they have a OS resolver. okay, which has a cache of recent DNS lookups. So your operating system, say you are using a browser on your Windows, so Windows has this its own local cache. Apart from the browser cache that we discussed earlier, there is also operating system level cache which will maintain the recent DNS lookups. Okay, just in case it is present there, you will simply get the IP address from it. You don't need to go further steps because it will save your time. But in case it is not even present in your OS resolver or local cache, you move to the next step, which is the step number 3. And the step number 3 is host file or the local override. So before going to the external DNS, OS will check the local files. For example, in Linux or Mac, it will check like this etc under host, or for the Windows it will check in the C Windows system 32 drivers etc host. Why we are doing this? Because each step will add a latency to it. The more you go to the lower levels, there will be higher latency and it will be a slower response for the end user. We want the response should be very quick for the end user. Like you write google.com and you press enter, it appears instantly, right? So for that you want to have like cache or local overrides, all that stuff. So just to show you this URL, as I'm using the Windows, I have opened the same one here. You can see C Windows system 32 drivers etc, and inside that there is a file. You can see it here, host. If I open this for you, you can also check in your operating system and then you can try to open this as well. It will show you some of the mappings that it contains, like what is the host and corresponding to that what is the IP address. So it is present in this. So this is the step number 3. Just in case we don't get it from the browser cache and in the local cache, then the operating system checks in the local overrides. Now let's say even if it's not present in this path like etc host, then comes the step number 4, which is the recursive resolver, which means the DNS server. Okay, if you're not able to find things in the cache and even locally, then the operating system sends a query to DNS recursive resolver. Now a question may come like, who provides this DNS? Generally it's like your internet service provider, that is the ISP. It provides you DNS, or there can be the public resolvers like Google DNS is there, which has the IP of 8.8.8.8, or there is Cloudflare, or there is Open DNS. So in case you are not able to find anything in the cache or in the local storage, you basically make a call to the DNS server to identify the IP address of that particular host. And now that we are reaching the DNS server, let's understand how the DNS server will provide you the IP address. So it uses something called as recursive resolution, which basically means that it queries the DNS hierarchy. The first step is the root DNS servers. So basically what it will do is the break down your host. So this was your host api.example.com, right? So what it will first do is like try to identify .com TLD servers. Where are they present? So it will try to identify using the root DNS servers. So as an example, you can clearly see, I don't know api.example.com, that I don't know this complete host, but let me ask for the .com servers. It's similar to that. If you're given a big task, you try to break it down into smaller tasks and perform that from the very beginning level, right? So in case it's not able to identify the complete host, what it will do is like first try to identify .com servers, where are they present, right? After that comes the next step, which is the top level domain servers. Once you have your .com DNS servers, you want to know where the example.com servers are, right? You have fixed this step. So next step is like example.com. You want to know about that. And then the next step is even further to find out the complete api.example.com, because you have identified this, then you have identified this, and then you go to this step, right? These are basically managed by the domain owners. So here we have already identified example.com. So these high level servers will be managed by the domain server, right? They know the actual A record or 4 times A record. so it will provide you the complete IP address. So we want it for this host api.example.com and say it will return 203.0.113.25, right? Now once it returns you this IP, what will also happen is we will add it to our cache, like in the browser cache as well with the TTL. This will be added so that the next time you try to hit api.example.com, you don't need to go till the fifth step, right? You can find it simply from the browser cache directly, right? So this is a flow. This was particularly for the DNS server. It is using the recursive resolution approach. Start from .com, then example.com, then the complete api.example.com. It tries to identify the IP address like that. Well, I understand this is too much information. Like, how will you get the IP address from the host? So let's see this with an example so that you can get more clarity. Okay, let's say the API call is something like this. Our main focus would be on the host part. This is the host, this is the protocol, and this is the URL part. So our focus would be on the host. So firstly, what will happen is, like, the browser will check its DNS cache. Like, it will check whether api.example.com, its IP address mapping is present in the browser cache or not. Let's take a case where it is not found. Okay, so just in case it's not present in the browser cache, the step 2 and step 3 comes at the OS level, which will first check its local cache and then the host file as well. I displayed you the host file example. It was like for Windows, it was present in C, Windows System 32 drivers etc. There is a host file. It will check the mapping here. If the IP address is present for the corresponding host, it will check it there. Just in case it is not found, we'll go to the next step, which is OS reaching out to the DNS servers, right? DNS can be provided by your internet service provider, or in generic the public ones, the Google DNS or Cloudflare. And then what it internally does is this flow. The DNS server performs the recursive resolver queries. First it will check for the .com servers because we wanted to check for api.example.com. Let's break it down. First it will check for the .com, then it will check for the example.com DNS server. And once you have this information, it will go to the higher level, which are managed by this example.com only, and that server will tell you the complete IP address of this host. Okay, so once we have this, it is returned to the browser, and browser will also maintain this mapping in the browser cache. So on the other hand, now we got the IP address, so the request can be hit on that particular IP address. Till now we just had the name, but we wanted the IP address because internet understands the IP address, right? So now you have the IP address, you can call that, and at the same time now it's also present in the browser cache. So say next time you made a call again to this api.example.com, you don't need to go to this level. You will simply find it out in the first level, which is your browser cache. So it will be pretty quick, right? Okay, so this is how your DNS works. So this was a step 1. Like for example, we said this will be your client. Whenever a request is made, first it goes to the DNS, right? So that it can provide you the IP address of the host. Now when I read about DNS in the beginning, I had a few questions in mind. So I'll discuss about those questions because maybe you may have the similar questions. It will for sure clear some of your doubts. And in case you have some more doubts related to DNS, what's the functionality, how does it work and everything, you can put that in comment section. I'll try to help you out. But for now, let's go through some of the doubts that I had during the time when I learned about DNS, and let's discuss about that. So the first question is, like, there only one DNS through which all this happens? The answer is no. So DNS is a distributed system with thousands of servers around the world. So it's not just one machine. There are thousands of servers which are present around the world. There are providers like Google Cloud DNS, AWS, Akamai. They maintain the DNS servers globally. So now just imagine, like, you are present in India. From your mobile phone you are using some application, or from the browser you are using some website. So from there, say you query api.example.com. So now it doesn't always go to the US. It will be basically routed to the nearest DNS resolver. Okay, so So for example, any DNS resolver which is nearer to India as compared to what present in the US, the request will be routed to this one because it is near to this. So what technique or logic is used for that? Anycast. So anycast is the technique or the logic, you can say, via which you are routed to the nearest DNS resolver. So here are a few examples. Say you are in India, the query goes to the Cloudflare's DNS in the Singapore. Here we just took an example that Singapore is nearest DNS resolver which was present to India. If in India only there is a DNS resolver, it will go to that because it will try to pick the nearest one. Okay. Similar example, someone is in London. So the query goes to the Cloudflare's DNS cloud in London. Okay. So it will try to find out the nearest one. Why do we want to find out the nearest? Because as far you travel, the latency would increase and you want to give the best user experience to the end user, right? So you always want someone entering api.example.com, so it should be very quick, like it comes really fast, right? So you want to give that kind of experience. So in order to have that, you want to provide the nearest DNS resolver so that it takes minimal time. So yes, like we discussed here, so these people, like one in India, other in London, so two different DNS resolvers would be trying to answer the same domain, but possibly they would return a different IP because the location is different. So you need to understand, like if we are talking about the gateways or the servers, as we know in system design, we need to maintain like distributed system. We can't be relying on only one machine because then it's a single point of failure. Why? Because like say that machine stops working due to any reason, it crashed or some other issue, whatever can happen. So in case that machine goes down, then your complete system will go down, right? So you have multiple servers, multiple machines, multiple gateways, everything is like distributed. Okay. Similarly, you saw like even DNS, it's like distributed system. We don't have single DNS, it's like multiple DNS. So now that you know there are multiple servers present, you also need to make sure those servers are distributed across the globe. Why? Say for example, you have multiple servers only in one region and there is some natural disaster like volcano eruption or tsunami or earthquake or anything like that. So what will happen is like that particular area is completely affected and all of your servers will be affected with that. So it may happen that all the servers stop working because in that area some disaster happened, right? So due to that reason, you want to have your basically servers, your machines distributed across the globe, across the world, so that you are not impacted by a particular thing that happens to a region. Similarly, one more benefit is like if a user is trying to use your server, so the nearest server can give the response and that would decrease the latency. Hence it is always recommended to have your systems across the different regions. Okay, so that's why when we say there are different machines in different regions, their IP address would also be different. So even though the DNS in Singapore or in London, it's trying to provide you the IP of this host, although the domain is same, but it may return the different IP because the machine, the gateway, anything that you can say is located in different location and they would have a different IP address, right? So the main logic is DNS is also distributed. It's not only one machine which is serving the complete world. It's like thousands of servers which are spread across the world. Now after this, let's move to the second question that I had in my mind. So that was like how request is routed to the nearest DNS. Although I told you like it is done using the Anycast technology, but let's try to understand this more. So basically it uses Anycast networking. So as I already mentioned you, there are multiple DNS servers worldwide. So you have internet routing protocols, okay, that automatically route your request to the closest available DNS server. So that means that you don't have to choose the closest DNS. The internet routing does it for you. So whenever there is a request, the ISP or the internet service provider, it will check for the nearest or the closest DNS server and it will query to that. Now you may have a doubt in mind like, from the DNS, how will it return the nearest server? available, right? For example, as I said, for my business, I may have multiple servers, multiple machines which are present across the globe. So there will be multiple gateways as well. Gateway we will discuss later in this video only, don't worry about that. But just imagine you have multiple machines which are present across the globe. So how does the DNS know which IP address of the gateway to return? We will talk about that, but for now you need to remember that in order to identify the nearest DNS, anycast networking technique is used. Okay, and now let's move to the next question which I was talking about, like how DNS will decide which server IP to return. So basically it's a magic of geo DNS or latency based routing. So the DNS will look for few things. First is a resolver's IP and approximate client location. Okay, and then it will do the latency measurements, like which region is fastest right now. Okay, so it will maintain all that stuff. And the third part is it will also check the traffic policies that you have configured, like you can have the weighted routing, failover, etc. So all those things it will keep in mind to identify which server IP to return. But the simplest thing you can imagine is, like, say for example you are in India, it will return the IP address of the Mumbai server. Okay, because we imagined here, like for India we have kept the server in Mumbai location, so it will return the IP of that one. So if you were in Europe, it would return the Frankfurt server IP address. For US, it would give you the server address which is present in US, and like that it will provide you the IP address. So basically just imagine, like we called https api.example.com from these various regions like India, Europe, US. So the DNS will automatically point to the nearest regional API endpoint, right? So it means, like when you are calling the same host api.example.com from different regions like India, Europe, US, it may return you different IP address. Why? Because it is returning you the IP address of the machine which is nearest to you, and based on different locations, each of the machine will have a different IP address. So you will get a different IP address, right? But all this magic is handled by the DNS. But now in case, just imagine like we had these three servers, okay, and one of the servers, but say the server in Mumbai, it stopped working due to some reason. Okay, now whenever there is a request from India, it won't redirect to the Mumbai server because it's not working. So DNS will keep a look on that this server is not working, so it won't give you the IP address of that particular server. So what it will try to do is it will provide you the next nearest server. So instead of US, it will provide you the Frankfurt server, because Europe is still nearer to India as compared to US. Okay, the more you have to travel, the more latency you will get. So that's why it will try to give you the most nearest working kind of server, right? So all that things will be taken care by DNS. And of course, like we reached to this point, like going to the DNS server, because it wasn't present in our browser cache and the OS level cache, right? The steps that we discussed earlier. But once you get the response, like the IP address from the DNS, you will save that in your browser cache, so that next time whenever this same API is hit or the same host is hit, you can return that from the browser cache directly. You don't need to hit the DNS server. But with that, we also need to keep in mind that there is some TTL, that is time to live, which we apply to the browser cache. Why is that required? Like there can be many reasons. One of that can be like just we discussed. So you are in India, right? So you hit this API, say api.example.com, and then what happens is, like maybe that wasn't present in your browser cache, and through the DNS you get this IP address, so 52.66 point something something. So you get that, and then you put that in the browser cache, right? So say like after 5 minutes this server stopped working, but next time the user enters or hits this again api.example.com, this was present in your browser cache, and you would simply redirect here, because you won't go to the DNS and you won't get to know that this is not working for now. So you will try to hit this and you won't get any response, which is not correct approach, right? So that's why, and many other reasons, we generally use the time to live, which is, you can say, expiry of the cache. So just imagine, for example, we have it like for 1 minute or so. So within 1 minute, if you hit the same URL, you will get it from the browser cache. Otherwise you will hit the DNS server, right? So like, it was just an example. The TTL, or the expiry of the cache, is basically any time that is set, and within that time, if you hit the same host again, it will pick from the browser cache. But in case the TTL time has crossed, then of course you need to go to the DNS server to find out the corresponding IP address. Let's try to understand this with an example. Say for example, you made a request from India, right? So you are in Delhi and you hit like https api.example.com/users/123. So basically this is your host and this is your URL or your path parameters, you can say. So basically the first step would be like, the DNS will try to help you to provide the IP address. You can go to the browser cache, say we don't get it from there, and then for the local cache also we don't get, then basically we go to the DNS resolution. Okay, so the query goes to the Google DNS, say for example, and the IP address of Google DNS is 8.8.8.8. Okay, then further Google DNS forwards it to the Cloudflare or the AWS Route 53 servers. So then what will happen is like, your query will reach the nearest DNS server which is available. Say for example, you hit it from Delhi, it will route it to Mumbai. Okay, and how does it do that? Using Anycast technique. Now once it is with the DNS, now responsibility of DNS is that it returns you the IP address of the nearest server available of that particular host that we hit, like api.example.com. It may have many servers, one in India, one in Europe, one in US, and many other, right? So the work of DNS would be to return the IP address of the nearest one. So what it will do is like, return you the Mumbai API server, say 52.66.x.x. Now how does this happen? Using the techniques, you can say the nearest server which is available, then the least latency, and some other parameters, traffic bound, like that you may have applied, that we just discussed in the above section. So all those things it applies, and based on that it will provide you the nearest IP address of the server. And once you have that, you can have the further flow of the networking layer, where you can build a connection using the TCP and TLS, and then further the things comes up like the gateway, load balancer, firewall, and then there is further flow which we will discuss later in this video. So the main point is like, once you hit some URL, so it will try to reach the nearest DNS server using the Anycast technique, and then further the DNS will try to return you the IP address of the server of the host that you have hit, which is nearest to you, so that you have the least kind of latency available, right? So in this example, you can say you made the API request from India, and the DNS is making sure that it stays nearby or within India. It's not going to the far away regions like USA, because if you go to that far, you may encounter a lot of latency issues. Now in the same example, just imagine that you hit this from USA instead of India. So here we said it was from Delhi. Say now you hit the same one, api.example.com uses 123 from say New York in USA. Then the DNS, what it will try to do is like, instead of Mumbai API server, it will try to provide you a API server which is in US only, or at least which is nearest to that region, you can say, right? And based on that, the IP address would vary as well, right? So in one case you are getting say 52.66 point something dot something, whereas if you hit that from US, you may find out some different IP address like 3.80 dot something dot something. So the basic point is like even though you are hitting the same thing, you may get the different IP address based on the location, because each of the gateway will have the different IP address, and the DNS will give you the IP address of the nearest thing which is present to you, right? So one more responsibility of DNS is that it will keep having the health checks. Say for example, for the Mumbai API server, whether it's working fine or not. Just in case it's not working fine, it won't route the request or provide the IP address of this server. Instead of this, it will try to identify the next nearest server available and return the IP address of that particular one. So that is also one of the responsibility of DNS. Now apart from this, I had few more questions in my mind while I was reading about the DNS. So one was like, who actually provides DNS? Now for now you may feel like we are talking in detail too much about DNS, and we are not talking about the complete flow, how the things work, but I wanted to make things in quite detail so that you understand the basics and the fundamentals, so that you understand what is DNS, like how does it work, who provides it, who pays for it, all that stuff I'll talk about. And after this, like I'll also talk about the other components. The other components are going to be the TCP, the TLS, firewall, gateway, load balancer, and then finally the server and your database, right? So in this video we'll talk about everything, so don't worry if you think we are just getting focused on the DNS. I just want to be sure that you get good knowledge on this part, because I did not find much of the resources in one go, like from where I can understand the complete picture. So I'm trying to build that. Yeah, so let's talk about DNS a bit for now, and after that we'll move to the next components, and at the end I'll provide you the complete kind of structure, like how the flow goes. And yes, by the end of video you'll have the great understanding of the complete basic structure of the system design. So stay with me, okay? Yeah, so coming back, who provides DNS? So basically there are three major layers in DNS. So first is the public DNS resolvers, which is for the end users, like you are using the internet and everything, right? So basically these are the DNS servers your device will query when you type a domain. Say you enter like google.com, yahoo.com, facebook.com, whatever. So in that case, these public DNS resolvers are called. Basically some examples are, as I said earlier, Google DNS is one which has the IP of 8.8.8.8. then you also have the Cloudflare DNS, which has 1.1.1.1. Open DNS is there, and then ISP DNS, that is your internet service provider, which also provides you the DNS. Okay, so these are free for the users, you don't pay for these directly. Now who provides that? Like companies like Google, Cloudflare, ISP, they run them to improve the user experience, right? Because they want you to use the internet, right? So the experience should be good. So that's why these companies provide this kind of experience. So this was the first layer, which was the public DNS resolver. Now let's talk about the other two layers. The second one is basically authoritative DNS servers, basically for the domain owners or the API providers, right? So say for example you created a domain like example.com, then you basically choose and pay a DNS provider to host your records. Okay, some of the example of these players are like AWS Route 53, which is by Amazon. Then you have the Cloudflare DNS, Google Cloud DNS, GoDaddy. You might have heard about this. There is a lot of advertisement of GoDaddy. So basically it provides you a domain. Say you want to have a website or anything, so it provides your domain, so you pay for that part. Like who pays for everything part we'll cover after this question, but for now you can imagine this is the second layer, because the first layer was like you as an end user, you are just going through facebook.com, you just want to log into your account and see some of the stuff. So basically for you, you had the first level, right? Where it was completely free, the public kind of DNS resolvers are come into picture. But this second one is like, if you want to basically have a domain, right? Your particular domain, you are building your website or something to which user can open or hit this domain. So for you, this second level comes, and you can pay to these DNS provider so that they can handle your stuff here, right? So just an example, if you run an API, like your API, this is your API, api.example.com, you add an a record in the DNS provider that maps your API server's IP, right? So for example, like you are creating a new domain for that particular domain. In the DNS, you want to keep the IP address mapping, right? So for that, this level comes into picture. And then after this, we have the third level, which is the root and TDL DNS server, which is for global infrastructure. Now you may ask, like, why is this required? So some big businesses, like you can say Instagram, Facebook, WhatsApp, YouTube, and a lot more, Amazon. So they have like usage in complete world, not just in a particular country. It's like spread across the world. Okay, so you want the global infrastructure. So these are managed by organizations like ICANN or IANA and the regional internet authorities. Okay, these are funded by domain registration fees and large internet bodies. Okay, as an end user, you don't directly interact with these. They are the backbone of DNS hierarchy. Okay, so like in short, if you can say, if you are just an end user who is just trying to open or log into an account and use some of the services of some other company which has that complete service, right? So for you, you will be using this public DNS resolver, which is like free for you. You don't pay for anything like that. But in case you are building your own stuff, you have your domain, then of course these things come into picture. If you are, say for example, for GoDaddy, you can have your host name specific that you want, and you pay for that part, and basically you provide the mapping here kind of for your you create a record and for your domain, and it will map the IP address for that part. And similarly, you may require the global infrastructure if your business is spread across the globe, right? Yeah, so with this I had more questions like who pays. Although I have discussed a few of the things in this only, but I had all these questions in my mind when I was checking about DNS, because it's not something that you interact with daily, right? Say for example, you understood like the client, okay, the mobile phone or your laptop on which you have the browser from which you are using a website, that's a client. Or from the mobile phone, you have the application, you are using the application, that becomes a client. That's fine, easy to understand. Even for server, as I told you, you can understand this is a computer machine in which you have written some code or logic that will get hit. But DNS, it doesn't like you don't get complete picture or understanding what is a DNS. So I had all such questions, so that's why I'm discussing with you, because maybe you also have the similar questions like who pays for DNS, right? Like how is this existing? Someone would pay for it, right? It can't be something like it's just happening by its own, because it's providing you the mapping. So who is doing all that stuff? Like for example, who is paying for that? So let's understand that. So as an end user, as I told you earlier, you would be using the global DNS kind of stuff. So you don't pay directly, right? So you're not paying anything to Google DNS or Cloudflare DNS. It's free for you because you're just using the services. It's not your service, it's not your business. So you are just simply using it, and in order to make your complete experience good, the Google DNS, Cloudflare DNS, all that, they are providing you all this experience, but you don't pay for it. It's completely free for you. Okay, so as an end user, you never pay for DNS, right? But the other case, if you are the API owner, say for example, you have the company or you are doing some development work, you want a particular host or anything like that, so you pay to the authoritative DNS, the second layer that I told, right? This one, as an end user, you don't need to pay because you're using the public DNS resolvers. This just is provided for free to you for the user experience. But in case you own an API, you have a business, then for this you need to pay. Okay, here you can see you pay to the authoritative DNS, right? So if you buy example.com from GoDaddy, you pay yearly domain fee, which may be anything like $10 to $15 per year or something like that, but you pay for that, right? And just in case if you want the advanced DNS features like global routing, health checks, failover, you pay providers like AWS, Route 53, Cloudflare, Akamai, right? The cost is not very high, it's generally small. For example, the Route 53 would charge you like $0.5 per hosted zone per month per million queries, but you need to pay for that. So basically, if you own something, so basically if you own an API, then you need to pay to this, the second level. But also at the same time, if you want the advanced features like the global infrastructure, you pay more for that part, right? As I explained it to you, right? So just an example, say you are building api.myapp.com, whatever, just an example, you can imagine any other domain or anything. So you will register the domain at GoDaddy. GoDaddy is just one example. There are other players as well, as we discussed earlier. But if you are registering something, you need to pay them. Okay. Like for example, $12 per year. And then basically host the DNS records on AWS Route 53. There will be some more cost for it, and then even for the global DNS, the global features, if you want like DDoS protection and much more, then you may pay for more on that part. So basically, end user, it's completely free. If you own a business API, so based on the features you require the domain, you pay for that, right? So when you pay for GoDaddy for your domain, it includes the DNS kind of fee, right? So this is how this happens. So that's why it's a good question to have in your mind, like who is paying for that? Like it can't exist by its own. Like it can't be like someone is just giving you for free. It can't happen. So someone is paying. Who is paying? The people who have their business, right? For example, if you are making a new company and you are registering a domain like mohitchabra.com, okay, anything like that, I need to register that. I need to go to say a player like GoDaddy or whatever, and I'll pay yearly fees to them. That comes to the second level, and say mohitchabra.com, it becomes like really famous, like worldwide. So I need more features for that, right? So that it is accessible across the world, and then some more features using the Akamai and all that stuff. So I'll pay more for that part. Yes. So as a business owner, as a company, or as you develop things, the some API or host that you require, you pay for that. So that is how the DNS is working, because some of the organizations, the business players, or anyone who is having the business, they are paying for it, right? I hope that makes sense. But just in order to make things more clear to you, you can imagine like the how much you pay depends on your setup. Okay, say for example, you are creating a very basic kind of API. So there are many cloud providers like AWS is there, and then there are many others as well. They will automatically provide you a default domain. Just example, like you can say if we use Heroku, it is providing me myapp.herokuapp.com. So in that case, because it's a default subdomain, they handle the DNS by themselves. You don't even need to think about it, because you just created a default subdomain from some other cloud provider, right? But if you want a custom domain, say for example, we talked about api.example.com or mohitchabra.com, whatever, then you must set up the DNS by yourself. Okay, if you want global low latency APIs, like you have the big business across the globe, then of course you will buy or register a domain. Then you set up the DNS records like A level and all such things. There can be multiple things where basically you set up the records, have the mapping, and you would also like to use the geo DNS or the latency based routing if you want the global traffic optimization, right? Because you want to give the best user experience to your end customers, so you would like to have those advanced features. And then you will pay for the DNS provider service like the AWS Route 53 or the Cloudflare. So depending on your setup, like for example, you're doing for development or you're building your business, even in case of business, it's kind of like small business or you are spreading across the world. It would depend, and you would pay according to the features that you are using, right? All right, so we talked a lot about DNS. So till now, here we are. So this was our, you can say, the client. Okay, the client is this, and this was your server, right? So let me put here server, and then of course you have the database here as well, which would like interaction with the server, you can say. Okay, so this is the part we said, like from here you will make a request API. For example, we said from here you had the API request, and then basically you will get the response, right? But in between that, I added you a component as the DNS. So what is DNS doing? So in summary, basically what's happening, whenever you hit some host from the client, which can be api.example.com, internet understands the language of IP address. So how will you get the IP address? The answer is DNS, right? So first step is your DNS. Whatever your domain is, the host is, it will first check in the web browser. If it doesn't find the IP address there, it will check local cache. Even if it doesn't find out, it goes to the DNS server, where it checks for the recursive calling to identify the IP address. The request goes to the nearest DNS server using Anycast. Okay, Anycast technique is used, and the DNS will provide you the IP address of the nearest, you can say, machine available. Okay, and after this it will provide you the IP address. Once the client has the IP address, it can build a connection. How does it build the connection? Using TCP TLS. Okay, so we will now talk about TCP TLS, and after that we'll go to the next step. So till now we have reached this point, right? All right, so let's talk about TCP, right? Like, what is a TCP connection? TCP connection is basically a three-way handshake. So basically TCP, you can say, the transport layer. It establishes a reliable connection before sending the data, right? So before going to the steps like how this connection is made, let's try to understand why do we use TCP. We use it because of the following reason. It's reliable. It ensures no packet loss. Okay, so for example, from the client side, you are sending something, it makes sure it reaches the server, so there is no packet loss in between. Just to give you the overview, there are other protocols as well. Say for example, the UDP is there. We'll talk about it maybe in this video or in some other video, you can say. That's also one of the protocols. But why do we use mostly TCP? Because as I said, like, it's reliable, it ensures no packet loss. So a lot of APIs that you use in day to day, and even in the development work, when you are doing the backend development and stuff, you will see most of the time we are using the TCP protocol, because it's reliable. Like, you are sending something and it's making sure that nothing get lost in between. An example of UDP, from where you can get some more understanding, is that UDP protocol is used when you are doing the video calls. Say for example, you are doing a WhatsApp video call where two people are talking to each other and able to see their faces, right? So in that case, UDP is used, right? But the problem with UDP is that there can be some of the packet loss. Okay, so few times you might have seen, like, you are talking to someone on the video call, and in between some of the things get lost, right? Some of the frames, some of the audio as well, so all that stuff happens. So that is the designed approach, because it is using UDP because it's faster in that way, because it's not forming that kind of connection, so it's fast, right? And that's fine actually for video calls, because you generally focus on the current view only. So even if some of the frames got lost in between or something, now you can see the other person and you are talking to that person, so it's fine in that. And also you can't have too much latency while you are doing the video call, because the main funda of video call is like real-time experience, so that you can see that person at that time and interacting with that person, right? if in case at that time there is huge delay, if you're getting the voice or the video after some time, like even like 5-6 seconds, it becomes really irritating and you won't do the video call. That's why we do use UDP, which is fast kind of stuff for video calls, although some of the packets may get lost in between. But in generic, most of the other applications that we talk about, we don't want that kind of experience, right? We want that it is reliable, so that whatever we are sending, it reaches that other place, it is not lost. So for that we use generally TCP protocol, okay, to send the data. These are the protocols, so we are using TCP most of the time. UDP also, as I told, for video calls you use that, and some other features you can say. So TCP, it's reliable, right? No packet loss. Then order delivery is another thing, right? Like say for example, you send things in an order, like first this, then this, then this, then this. So that order is maintained in TCP. As a client, you are sending something in some order. If you want that order, it goes also in the same order, the order is maintained, then TCP is the protocol for you, okay? And apart from that, it also does error checking, like it detects some of the corrupted packets and all that stuff, and it gets resent, right? And it is connection oriented. Once the handshake is done, both sides know that they can talk, right? So that's why HTTP and HTTPS usually run on TCP port 80 or 443, right? So the main point you need to understand is that once you have the IP address, you need to build a connection in TCP. It's not like you can directly send the data. Say for example, from client you are sending an API request like api.example.com and sending some whatever query params or body. It's not like you can simply directly send it to the server because now you have the IP address that you received from the DNS, right? No, you can't do that in TCP. For TCP, you need to build a connection first. Once your connection is built, after that you can send the data, but you can't send the data before making a connection. So that's why we are talking about the TCP connection, like how this connection is made. Why is it required? We just talked, it's reliable, no packet loss, order delivery and all that stuff it takes care of. It's a really famous popular protocol which is used most of the times. So TCP is that one. Now as I said, you can't send the data directly in it, because in order to satisfy these conditions, like in order to make it reliable, in order to make it order delivery, it needs to make a connection, right? And after that you can send. So that's why connection part we are coming on. So TCP establishes a reliable connection before sending data. Before sending data, you need to make a connection, right? So what are the steps? So first, the client will send to the server SYN, which means client is kind of saying, hey, I want to connect, right? And the server will send back to client SYN-ACK, okay, which is kind of server is saying, okay, I got your request, ready? It means it is acknowledging that I got your request. This is not your normal request like in which you are sending your data, right? It's not that one. It's for the connection buildup. First, it will build the connection using these steps. Once the connection is built, you can send your whatever request, your data having whatever things are there. So the second step is server will say, I got your this SYN or the sync request. Okay. Now I am giving you acknowledgement that I received your sync request. Okay. Are you ready? Then it's a three-way handshake. It's not like client side SYN and it said like SYN acknowledge, so it happened. No, it's a three-way. Third step is client will again send to the server ACK, which is acknowledgement. So the client is saying confirmed, let's start. Okay. And once these three steps happen, the connection is established. So three-way: client, server, sync, sync acknowledge, and then again acknowledge, right? So three steps: client to server, server to client, client to server. Based on this, your complete TCP connection will be built, and once your TCP connection is built, you can send the data, right? So yeah, let's talk about more things in TCP. So once you establish the connection, now you can do the data transfer, right? So once the TCP connection is live, the client can send the HTTP request data like headers, method, body inside the TCP packets. So basically we are using the TCP protocol, so the data will flow using the TCP packets. Okay, the server will process it and send back HTTP response inside the TCP packets. So now you understand like how the data flows. The data will flow basically in TCP packets. Even the client will send it via the TCP packets and the server will send via the TCP packets, because we are using the TCP protocol here. Okay, what is the TCP protocol? We just discussed about all this stuff, right? It will build the connection and then send the data via TCP, reliable order delivery, all that stuff. Okay, so via this will go. Although this is not the only step, we'll talk one more step, which is the TLS. You'll get clarity about that, don't worry. But for now you can understand, first you need to build TCP connection, then the next step as the TLS, we'll talk about that, don't worry. Okay, so one more thing, like the connection closing. Okay, as we said, like we first need to build a connection before sending the request. So you're building a connection, so you also need to close the connection, right? So basically when the exchange is done, one of the party will send finish, FIN, and the other side will reply with ACK, that is acknowledge, and finally the other side sends its own finish acknowledge. Okay, so the connection is closed cleanly. Like it is very similar to what we did earlier. So say for example, this is the client, this is the server. First, in order to build the connection, it send SYN. You can say like sync, it wants to sync, it want to interact, you can say. And then it will say, the server will say sync acknowledgement. I am writing the shortcut here, although it will be SYNACK. So sync acknowledgement from the server, and then client will again send acknowledge. Okay, so this is how your connection is built. Now in order to close, say for example from the client side you are sending FIN, that is you are making a request to finish the handshake or the connection. And then from here it will come like ACK, that is the acknowledgement, and again from this side it will come finish acknowledged. Okay, again 3 step, similar to what we had earlier, same way we are closing as well. Okay, so now again, like when I understood the concepts of like TCP, where you need to build a connection before sending the request, and then there is finishing of the connection, I had some of the doubts that I'll discuss with you. Like what were the questions in my mind and what is of course the answer of that. So it may help you because you may have the similar kind of doubt. So the major doubt, that as I said, you need to make a connection before making the API request. So is it that for every API request that you are sending, you need to make a new TCP handshake? So for example, now that you will be a backend developer, right? And there will be multiple APIs, right? And it can happen that the client needs to hit many APIs. So first is like say your user feed, and then your profile API, and then some other search API, and a lot of things can happen. So is it that for each of the API first you need to build a connection, the TCP connection for each of them? So then it will be quite slow, right? Because first, in order to send the data, you need to build a connection, and then once the connection is built you can send, and then it is closed, and then the next time you need to again make a new connection. So the answer is not necessarily, it will depend on how the connection is managed. Let me explain it to you. So let's talk about different type of HTTP, right? And based on that it will vary. So the old days, talking about, it was like HTTP 1.0 or 1.0, you can say. At that time, for each of the requests you need to open a new TCP connection, just like we said, like you need to send user feed, so before that you need to build a connection, then you need to make a new search API, before that you need to make a connection. Okay, so every time you are making, say for example login, you need to handshake. For new API offers, before that you need to handshake. Purchase, you need to make a handshake. Okay, but of course it's very inefficient, especially when you have to do the long distances, because say for example your server is in like US and you're making call from India. So first time you're making a connection, it takes a lot of time, right? Because the request will go or travel a long way, right? So it will increase a lot of latency, and for every API request you are doing this, so it will add a lot of latency. It's a very bad experience, and that used to happen for the old days of HTTP 1.0, but not anymore. So with HTTP 1.1 you have this keep alive feature where you can reuse the connection. Okay, earlier, like in 1.0, there was like no connection reuse, so you used to make connection every time before the API call, but now in 1.1 you can basically reuse the connection. So basically for the first time, of course, you need to make a TCP connection, you need to build up on that, but after that the TCP connection will stay open for some time. Okay, so first time you make a connection, after that for some time it will stay open, and you can make the multiple API calls during that time, and they can use the same connection. You don't need a new handshake. For example, you created a TCP connection and then you can use the login API. It will use the just now created TCP handshake that you just created. Then the offers API, it uses the same TCP connection. Then the purchase API, it uses the same TCP connection, of course, until the idle timeout. Till the time your connection is alive, you can reuse that, and you can make the API call using the same connection. Okay, so by default HTTP 1.1 enables connection keep alive. Okay, and apart from that you also have now the HTTP 2. Okay, so it is built on TCP but supports multiplexing, which means like multiple API calls share one connection in parallel, right? So in 1.1 things were happening in sequential, but in HTTP 2 you can send the request using the same connection in parallel as well. So login, offers, purchase, all these APIs can happen at the same time in one TCP connection. Here you said like first you are making a login request, then the offers request, then the purchase. Here you are also able to make the multiple API requests in parallel, and of course you are reusing the same a TCP handshake connection. Okay, and after that you also have the HTTP 3, which uses QUIC over UDP. I told you about UDP, right? Which is used in video calls. That is also protocol. So HTTP 3, it uses UDP instead of TCP. As I said, you TCP and UDP are the protocols, the famous protocols, you can say. Most of the times you will use like TCP, but few of the scenarios like video calls and other stuff, you may also use UDP. So for that you may use HTTP 3. Okay, now because HTTP 3 it uses UDP, and I said you like it's fast, you don't need to build a connection, and because you are not building a connection, it's fast. There are some issues as well. It doesn't assures you that the data will reach, so there can be some packet loss as well. So for that it happens, it's a part of UDP. But the good part is it eliminates the three-way handshake, because it doesn't do the TCP protocol, it is using its own stuff, right? So it's faster, great for mobile networks where connection drops. So yeah, so basically HTTP 3 uses UDP over TCP. HTTP 2, HTTP 1.1, HTTP 1.0, these uses TCP. 1.0, it was a old stuff, we don't use it because you need to build the connection, TCP connection, every time before the API. So you can imagine we won't use it now. These are the two things you can say 1.1 and 2 are there. So 1.1 supports reuse of the connection but in sequential way, whereas 2 supports like reuse of the connection, same connection, with like parallel API calls, right? So this was like, you'll get understanding. TCP connection you need to make first time, but it's not like for each and every API request you need to make a TCP connection. You can simply reuse it. Okay, all right, so with this we covered the TCP. Now let's go again back to the diagram that we were creating. Okay, so this was client server database. So the first step was the DNS. Let me also write it down, the steps, so that it becomes easier for you to understand. So this is the step number 1, and then you have your other thing, which is the TCP. Okay, let me write it down, the TCP connection you need to build. Okay, so also I need to mention it, this is the step number 2. Okay, so first from the client you go to the DNS so that it can provide you the IP address of the nearest you can say the server. Once you have the IP address, you have to build a connection, the TCP connection. Okay, and before sharing the data over the TCP packets, you need to build a three-way handshake connection in TCP. First you said SYN, then you get the SYN acknowledgement, and then you do the acknowledgement. So it's a three-way handshake between the client and the server. And once the connection is built, then basically you can send the data. But before that, we have another step, which is the TLS. All right, so now let's move to TLS. We'll discuss about that, but just a reminder, I'm putting a lot of effort so that all of us can learn and grow together. So just in case you have not subscribed to the channel, please make sure to subscribe the channel so that I get the motivation or the inspiration to make more such of the content where we can learn some of the concepts of system design, and we can learn things, we can grow, and you have the confidence to crack your dream company offer, right? So subscribe to the channel, like this video, and share it with your friends and family so that all of us can learn and grow. All right, so let's move ahead with the TLS. Okay, so first of all, what is TLS? TLS is basically transport layer security. In this also we will make a handshake. Now why this TLS handshake? So when you call an API, like say for example we talked about api.example.com users 123, okay, the browser or the postman. What is postman? So basically it's kind of a development tool, you can say, from which you can hit the API and see the response. So whatever API you want to hit, you will send the request to it and it will provide you the corresponding response. Okay, so it's kind of a mock, you can say. So it's a development tool for which you can see what is the response coming for this request and all such stuff. So either you hit it from the browser if it's public and everything, but in case you want to check it in development phase or all such stuff while developing or tools for debugging and all such stuff, you can also use postman. Okay, such a just a tool. So you can imagine you are making a API request, so it must ensure there is encryption, okay, which means nobody can read your data, right? It should not happen that in between some other person is able to see the complete things which are coming or going in the request and the response. That is the man in the middle. It should not be the case like you are sending the request to the server, but in between there is some other person who can directly see your data, right? So we don't want that, so that's why we want encryption to happen, right? And also we want authentication. As a client, we want, like, if you are sending it to api.example.com, the server should be actually api.example.com. It should not be some other fake case. It should not be the case like you are thinking you are hitting to that thing, like for example you are hitting on youtube.com, but actually you are going to some other place. It should not happen, right? Especially for the cases like you are making transactions on Amazon or some banking application or whatever, all such things. You want that it should be like first encrypted, then authentication should be there, and then integrity is also important. That means that data is not changed in the transit. Like for example like server sent a response, right, or the client sent a request. It should not happen there is a man in the middle who is changing the data, and when you get the data you think that you got this from the server, but actually it was modified in between. So all these things, these are very important, and you want that whenever you make an API request, so these should be taken care of. The encryption, that is that nobody else is able to read your data. If you are sending it to the server, only the server can see your data, no one else. Similarly, authentication, if you are sending request to the server, it should go to the actual server. It should not go to some other random place, right? And similarly for the integrity, that if you made a request or the response, the same thing should go back to the server or the client, right? It should not be modified in between. So TCP was just providing you a connection through which you can send your data in TCP packets, but we also need to make sure these things are also ensured while we are making the API, and that is done via TLS. Okay, Now let's talk in detail about like what are the steps that are involved in this TLS handshake. Basically you can simply understand it as like HTTPS. Okay, so say for example if I open google.com, okay, so you can see in the browser it says google.com. If I click on it, it will provide you the complete address. You can see here HTTPS. So this is, you can understand as the TLS thing that we are talking about. This is not just HTTP, it's HTTPS. Okay, because this is the step which provides you all these things that we talked about, the encryption, authentication and the integrity. Okay, so basically in this the TLS also has versions. So first we'll talk about TLS 1.2. Then there is also TLS 1.3 which is quite fast. We'll talk about that also, but for now we will discuss first about the TLS 1.2. okay, and then I'll tell you what is the difference in 1.2 and 1.3. Okay, so the first step, say client hello. So client says to the server via postman or browser or some other tool, you can say, from which you can hit the API. It says, hi, I want to connect securely. It sends the supported TLS version. Like for example, I said we are talking about 1.2 here. Then it also sends the cipher suits, the algorithms and the random number. Okay, so you can see an example like this here. So this is the client hello. It tells the TLS supported version. As I said 1.2, here you can see TLS 1.2. Then it also sends the algorithms here, and say for example AES 256, and you can also see here the SHA 256 that we are sending, and then there is also some random number, you can say R1 here. Okay, and then the next step is the server hello. So the server replies, it chooses the best cipher both support. Like it will choose from these cipher which both the client and the server are supporting. Okay, and then it sends its own random number, and then it also sends its digital certificate which contains the public key, the domain and CA signature. So I understand that these things can be like overwhelming for you. You might say what is this, like this algorithm encryption and all. So these are mostly part of the encryption, like how encryption is happening and everything. If you want to know about more about how this complete process happens, you can put that in the comment. I can create a separate video, because if I start talking about this now, then we will divert from our main topic of how the API works. For now you can simply understand that the TLS step is the HTTPS step, which provides you the security, the encryption, the integrity, and the other thing that we talked about, the authentication. So all three things, these are happening via this step of TLS. Like just giving an overview, yeah, we can talk more about it in the encryption part. So this is the sample from the server. You can see it will provide you whatever the algorithm it chooses, because both of these support these, and then it also passes the certificate and the random number. So this is a flow, don't worry much about it. It's mostly you need to remember there is a TLS step which works for the HTTPS, why it is required, integrity, authorization and encryption, right? So okay, let's move ahead. Don't worry much about it. If you want to know more, put that in comment section. I'll make a separate video where I'll talk more about what is encryption, how things happen, how is this complete TLS flow happens. Okay, so the next step, certificate validation. Client verifies if the certificate issued by the trusted CA or not, and it also checks for like whether the domain matches. Say for example api.example.com, it also checks like whether it is expired or revoked. If the validation fails, connection closed, and browser says it is not secure. Many a times you might have seen that the browser shows you it's not secure. It's mostly when the certificate validation fails. Okay, like again, if you want to know detail about it, how it checks the certificate and all that stuff, we can check that in the separate video. What I can show to you is, like as I said, when you click on it, you can see it says HTTPS, and when you click here it will say that google.com, the connection is secure. So when you tap on that, it will show you this lock sign, right? and the certificate is valid. It says that. Let's try to click it. You can see this is the certificate where we can see this says like the google.com and all that part here. It says issued on this time and expires on this time. So all those things, the certificate, fingerprints and everything, public key, everything is visible here. So even in the details you can see all that stuff. So this is kind of the certificate that I'm talking about. The expires on is there. So all these things can get checked, and in case it doesn't match, it can simply say it's not secure, right? So this is the certificate validation step, and then the fourth step is the key exchange. Now both sides agree on a shared session key for the encryption. Now because we talked about the encryption would happen in this TLS step, right? So for encryption you always require the key, right? For that to happen, where we are having the shared session key for the encryption. So there are two methods, RSA, which is the old one, and then there is one new modern method as well. The old method is like the client generates the session key, encrypts with the server's public key, because in encryption you will have the public and the private key. So here the client is generating the session key and it is encrypting with the server's public key. Whereas in the modern method, both client and server generate the keys, exchange and compute the same secret independently. Now again, you don't need to go in detail about this. If you simply say about the TLS step where you are securing this HTTPS, it's enough. But just in case, again, if you want to know more complete in detail about the encryption step and everything, put that in comment. I'll create a separate video on that part so that you get more understanding. So after this, the fifth step is the handshake finish. So basically both client and server will send the finished messages which are encrypted with the session key. We talked about the algorithm. Say for example, we are talking about this one. Say it will encrypt with the session key, both will decrypt successfully, and the handshake will be done. And once the handshake is done, from now on all communication between the API request and the response, this will be encrypted, which we wanted to do, right? So once this handshake is successful, so then basically you can send the data which will be encrypted, right? So this is the TLS step, you can say. As I said earlier, this complete flow that I talked about, this was for TLS 1.2. But now TLS 1.3 is also available, which is the modern and the faster way. Let's talk about TLS 1.3. So basically TLS 1.3, it reduces the handshake to one round trip. So you can imagine like in 1.3 we have only one round trip, whereas 1.2 there were two round trips. Okay. 1.3 also uses strong forwards secret key exchanges. So basically 1.3 is faster as compared to 1.2, and the TLS step basically provides you the HTTPS support, which makes the connection encrypted, which provides you integrity and authentication, so it makes more secure. So via using TLS 1.3, now we can say that HTTPS is now almost as fast as HTTP. But the good part is HTTPS is way more secure as compared to HTTP, because in HTTPS, using this TLS technique that we had added the steps like encryption, then we are taking care of the authentication, integrity, all that stuff. So that makes it way more secure. So we'll use TLS 1.3 and it will be quite fast and secure. So let's talk about one of the example in API flow so that you get more understanding. So say we made this get API call, which is to users 123. Okay, the first step, of course, DNS, it will provide you the IP address, all the things that we discussed about the DNS that will come into picture. But once you have the IP address, the TCP handshake will happen, because before sending data you need to build a TCP connection, and your data will also flow in TCP packets, right? So it's a three-way handshake that will happen. And once your TCP is done, you will do the TLS handshake that we just discussed. It is basically to set up the encryption. Okay, and once the TLS handshake is done, the request which we send is encrypted. So here you can see get users 123, it has the host here, so api.example.com, and then users 123. It has this authorization token, which is generally the JWT token. Yeah, we can talk or discuss more about the JWT token, how the authorization work. If you want to know more about it, you can put that in the comment section. I can create a separate video on the JWT token. But basically the main point is this complete request anything that you send in it, it is basically encrypted. Okay, so once the server receives it, the server decrypts it, processes it, and encrypts the response, because now server has to send the response. It also needs to make sure that the response is encrypted as well, and once it is encrypted, it is sent back to the client. Now you may think like we did not discuss TLS in complete detail, because I said like encryption and everything we can cover that in separate part, and I think that is not that much required when we talk about the how API works, but I'll provide you a brief summary. So here you go. So basically the TLS handshake, it basically establishes the secure channel. Okay, and basically it uses the certificates, CA, key exchange, so all those things it uses. And then basically TLS 1.3 is quite faster, safer, and which is the standard method to go today. Okay, and once the TLS handshake is done, all the API flows are encrypted over HTTPS, right? So this is the brief summary that you can get from the TLS step. So just to inform, CA here means the certificate authority. As I displayed you the certificate, you can check that on clicking on the log button, and it shows you the information related to it, right? So basically now coming back to our diagram that we were creating, right? This was client server database. The first step was the DNS. From DNS you got the IP address. Then the second part was the TCP connection, because only after having a TCP handshake your connection is built, and after that you can send the data to the server in the TCP packets, right? So after this, the next step that we just discussed was the TLS. So what TLS helps is in, it provides you the secure connection, right? So with this you can send the data over HTTPS, and there will be encryption that is happening to both the request and the response. So the encryption will happen, and hence it will provide you the security layer, right? So these are the first three components. We will talk about more components, but before that let me show you like how the request and response will look like. We saw those in brief, but let me also tell you some of the terms which will be part of the request and the response. So let's talk about the API request first. So this is an example of the API request. So you can see here get, and then you have the users 123. It says HTTP 1.1. What does this mean? So first of all, get, it is HTTP method. We talked about get, post, put, patch, delete, all these methods in this video. You can refer to this video to get more clarity about it. Okay, so basically it tells you the HTTP method, and after that you have this users slash 123. It is basically path on the server. Okay, the complete the URL that you tell, it contains, as I told you earlier, the host or the domain you can say, and after that it has the path parameters, right? It can also have the query parameters starting with the question mark and all, but basically these are the parameters which tell like what is the functionality that you are going to do, or talking about some of the information. Say for example you are passing the user ID here, so all such information we pass. Okay, and then there is HTTP 1.1, which is the basically the protocol version. I told you like HTTP had 1.0 version, the old version where you cannot reuse the connection, then 1.1 where you can reuse the connection, but you can make multiple API calls in sequential order. So 1.1 supports sequential multiple APIs that can reuse the connection. In 1.2 you can use multiple APIs in parallel using the connection as well. So here it says it is using 1.1 HTTP 1.1, right? And then basically this was the, you can say, the top link that you generally see on the browser, and there are some other things which can be part of the API which you generally don't see directly on browser. But in case if you want to check, what you can do is like right click on the browser, you can click on the inspect part, then the network layer. Okay, so say for example I go to images, right? So you can see multiple API calls and all can go. So say I click any of these, you can see this is the API request and response. Like this will be the response. When you click on the response, you can see the response here, and in the headers you can see this is the URL that I was telling you. In the URL you can have the domain, and then you also have the path parameters, right? This is the request method get, like I told you in my example we were using get. Similarly here it's a get. The headers part that I just discussed here, you can see it says the request headers here. The authority is google.com, method is get, path, and then you have all these things like cookie is there, what it accepts, all such information comes in the header. So similar information I was showing you in this example. Here we took like the host, which is the api.example.com. In that case it was google.com. Then it also had the authorization, which is generally the JWT token. We can discuss about it in a separate video. If you want to know, you just put that in the comment section. I'll create a separate video. Basically authorization is required so that every time you make a new API request, the server checks whether you are a valid user or not, if you have access of that or not, and that happens via this authorization JWT token, which is part of the headers. Okay, then it has the content type, which is generally JSON. Then you have the accept, which is also generally the JSON type. And then the user agent, it means like from where are you making this API request. For example, if you are making this API request from Postman, it will show Postman. If some other tool, it will show that thing. Okay, so this is the header. Header can contain all such kind of information. It can contain much more information as well, but the most important is like the authorization that you will see a lot of times when you are working on the APIs as a backend developer, right? So let me talk in brief about all of these. So host basically tells which domain, so it can be important for servers which are hosting multiple domains on the same IP address. Then the authorization, basically as I told you, to check or verify the identity of the user, and even to check like whether the user has access to it or not. Content type is basically the format of the body. Generally it's like JSON, but you can also have like text HTML, like we just saw in this example, because the response was also in HTML. So in this case the it accepts like text part as well. Okay, but in generic most of the times you will send the data in JSON format. Accept basically tells what response format clients can handle. Okay, mostly it will be again JSON, but in some of the things, like as I showed you, it can be HTML or some other format as well. Then user agent, as I told you, from where you are making the API request. Right now, apart from the headers, the request can also have the body. In the body you can pass the some of the information, like for example email ID and all that stuff, that other information that you need to pass, you can pass that in the body part. And whenever you put something in the body, it won't be visible to you on the browser URL, just like the headers. Okay, so one of the things is that in the get method you can't pass the body. Yeah, generally you pass the body when you have the method like the post, or the patch or something like that. So that's why I did not include the body part here. But yeah, if you are making a post request, then you can also pass some of the information in body. Good part in that would be, as I said, it won't be visible on the URL. So if you want something that is not visible on the URL, then you can put that in the body section, right? This all is fine, but the main part that I wanted to tell you was like how the things travel. Okay, so all of the things that we discussed, the request line means this one, okay, and then the headers and the body. Headers, I displayed you an example here. This is an example of headers. Body I did not display you because this was an get HTTP method. In case it was a post, I could show you the body, but body you can simply imagine it's a JSON that you are passing or sending to the server. So all of these things, these will be serialized into bytes. Okay, and then bytes are encrypted by the TLS session key. As I told you, the TLS will provide you the HTTPS support. Via TLS your everything will be encrypted. Basically encryption is done by the TLS session key. Okay, and then basically this encrypted bytes are sent as TCP packets. You remember that we created a TCP connection, right? The TCP handshake, three-way handshake, and we said like after that all the data, all the information will flow, the request and response, all the data will flow via the TCP packets. So this is the thing. Basically first all your request line, headers, body, those are serialized into bytes, and then they are encrypted because you are using the TLS HTTPS support, which provides you the encryption, and once it is encrypted, you send this encrypted bytes as TCP packets, right? And via internet you send it to the server, and then on the server TLS layer it decrypts it because you encrypted it. Then of course you need to also decrypt it, and then the further thing happens like HTTP parser reads and passes to the application layer, which is your backend code. But main part was this. I wanted that you should know about this part, right? So how the things travel actually. So now one doubt may come into your mind, like we are talking about like how data will flow, but actually how the packets move across the network. So I'll try to explain it to you, like how things work, so that you get some clarity around it. But it's not that important to know, but it's good to know kind of information so that you get more clarity in your mind, like okay, how things flow. So basically we talk about like how packets move across the networks. So when you send an API request, say you are sending get api.example.com, so the first step is the local routing. Okay, from your computer it goes to the default gateway, which would be usually your Wi-Fi router. You are connected to some Wi-Fi connection and router, right? So it first goes to the local routing, which is your Wi-Fi router. The router will check the routing table. Okay, if the destination is in the local network, it will deliver it directly, but in case it's not, it will forward it to ISP. What's ISP? It's internet service provider. Okay, so the step 2 is your ISP routing. So what will happen is like ISP router will check its own routing table, just like your default routing table. The ISP router will also check its routing table. It will decide the next hop, another ISP, or you can say like this, it will move to the next ISP, right? And then the step 3 would be the BGP. BGP is border gateway protocol. Okay, this is the protocol that connects the different ISPs and data centers globally, right? So basically internet is connected via various ISPs and the data centers. So this protocol, border gateway protocol, that will help you connect to the different ISPs, right? It will basically decide which path your packet should go to, right? Now let's try to see an example so that we can get more clarity. Say for example, we are currently sitting in India and sending a request to a server in US. Okay, so your internet service provider may route the traffic. It may go to like Singapore and then LA and then Google's data center. So if one path goes down, so BGP reroutes dynamically, right? So this is a protocol which works like it will provide you the path, but in case something is down in that path, it will provide you some other path, right? So that is the border gateway protocol. So this was an example of these 3 steps. Then after this, the step 4 is inside a network, right? So OSPF, that is open shortest path first. This protocol is used inside ISP's own network. So basically it finds the shortest and the best route between the routers within one autonomous system, because of course you want to take the shortest path wherever you want to reach, right? So that is handled by this, and then of course you reach the destination. So basically packets finally arrive at the data center, and this was a path. So in similar term, when we talk about the response, it will follow the reverse route back. Okay, so again, I mean, you don't need to go in that much detail, but just for clarity I told you like how the packets move. Like this is the system of internet. Each of the router has its routing table, and based on that it will decide the next ISP, or if it's in the local, it will deliver it directly. And then we also talked about the BGP, which is the border gateway protocol, through which it will connect you with the different ISPs, and of course algorithms like open shortest path first, so that you can reach to your destination in the best way possible, right? So this is how the packets will move across the networks in the internet. Well, I understand that this can be overwhelming, so let's see an example so that we can get some clarity about it in easy terms, right? So here is one of the examples. Say you are in India and the API is like related to US. The servers are in US, just for example. So first your laptop, then your Wi-Fi router, any IP address of your router, you can say 192.168.x.x. Then basically from the router it will go to your internet service provider. Say you are using Airtel connection, so Airtel internet service provider. Then it goes to the Airtel core router. From Airtel it will go to the peering router in Mumbai, because you have to travel from India to the US. It will keep on checking for the next ISP and the next path that is available. So say we are going to the peering router in Mumbai, anything say Tata Communication, and then it takes the undersea cable across the Atlantic fiber, and then it delivers to the US tier 1 ISP router, and then internet service provider hands a packet to Google's autonomous system, like via BGP that we discussed, right? Then the Google internal routers uses the OSPF, that is the open shortest path first, and then it finds the correct data center to the server. So basically you can understand your complete API request, it literally travels across the world in just milliseconds. So this is kind of the setup. Everything is connected across the world, everything is connected, there are different ISPs, and we use these algorithms and protocols to do that. Again, you don't need to remember all of the stuff, it's just to make things clear in your mind, like how things, or how the packet or the information flows in the API. Right now that I talked about IP address a lot of times, here also you can see 192.168 dot something dot something. Let me just give you a brief about that. So when I give this kind of example, this is an example of IPv4, whereas nowadays we also have IPv6. So let me take a minute to define both of these for you, so that you get more clarity on that part. So there you go, here is like IPv4 versus IPv6. Basically an example of IPv4 can be 192.168.0.1. it is basically a 32-bit address. So you can imagine, like, because we have three dots here, so each of these things would be 8-bit. So 8-bit, 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 and 8-bit. So hence what each of these can contain is like 2 the power 8, which becomes 256, right? So each of these can have numbers between 0 to 255. So these are the valid combination that can come here, because each of these is like 8 bits. So that's why this is a valid IP address, because everything here you can see is lying in this range 0 to 255. Okay, 192.168.0.1. so this is a valid IP address of type IPv4. But now because it's a 32-bit address, so the total possibilities of address is nearly around like 4.3 billion. It looks like a big number, but the problem is there are too many devices, and because of this there are not enough IP addresses, because a lot of devices are there, right? So it uses NAT, which is network address translation, to share the public IPs, right? But as I said, this was a problem in IPv4. Nowadays there is also IPv6, which provides 128-bit address. Here we only had like 32-bit address. Now in IPv4 these 32 bits were separated by dots, right? You can see 192.168.0.1, but in IPv6 it will be separated by colons, and it is hexadecimal. One of the example is this one, 2405 colon 204 colon 67, and you can see it's a big one, right? So the good part with this is like you have total possibility of like too much combinations that you can create with this one, and there is no need of NAT, because that was required to share the public IPs. But now that we have so many IP addresses, we don't even need the NAT. So each device can have a unique IP address using IPv6. Okay, it is built in better security, which is IP6, and it has more efficient routing. Okay, so if we talk about the APIs, both IPv4 and IPv6 work, but IPv6 adoption is growing, right? So you can see even IPv4 exists for now. You might see the IP addresses like this, but yes, IPv6 adoption is growing because it addresses some of the issues that were part of the IPv4, right? So I just thought of giving you a brief about the IP address, because I've mentioned IP address so many times in this video, so I thought it might be helpful for you. So with this we have covered like few of the things, like DNS is covered, then the TCP is covered, and the TLS is covered, and then some of the basic stuff that we talked about here and there. But after that we'll talk about some other components that will be involved before reaching to the servers, right? So let's talk about that. Okay, so till now we have covered few of the topics like DNS, TCP, TLS. Now before reaching to server we need to discuss about three more things, which are firewall. So let me write it down. Firewall. After that we will also talk about another component, which is gateway, which is a very important component, because in most of the system design high level questions, while designing your complete system design, you will mention gateway. And then we also have load balancer. Okay, we will talk in detail about each of these and why are they required. All right, and I will also tell you like how the complete structure will look like how are these connected. Okay, so we will discuss about all those things. So let's start with an example. Actually, say a user is in India who opens the application, and from the front end application we are making an API request. You can imagine like api.myecommerce.com, and then it has the path, also some query parameters. Okay, let's now try to understand the three components that we just mentioned: firewall, gateway, load balancer. Okay, we'll start with firewall. It acts as a security checkpoint. So what's the responsibility of this firewall? Its responsibility is to block any bad or unauthorized traffic before it touches your infra. In infra I mean everything like the load balancers, the server, the database, all such things, right? So what we are doing is like block any unauthorized or bad traffic in first go. So your firewall is acting as your security check post. Okay, now an important question comes is like, we understood what is a client, we understood what is a server, like, but what is firewall? So firewall basically works at the network level. Okay, which is L3 or L4 level. Now you may have a question in mind, what's L3, L4? So basically network has multiple layers. I'll show that diagram to you so that you get more clarity on that part. So basically you can see here there are 7 layers. First is physical, then data layer, then the third is the network layer, then the transport layer, fifth one is a session, sixth is presentation, and seventh is application, right? So basically the firewall works at these level L3 and L4, which is network and transport level, right? So because it is working on the network level, its responsibility is like block the traffic from the blacklisted IP ranges. Like you already have a blacklisted IP ranges, so it will directly block those before it even reaches your like gateway or load balancer or even your servers or database. Okay, similarly it can perform many such things, like in case the headers are malformed or the traffic is unauthorized, so it can directly block all of those. So you can imagine one more example. Say your the business or your application is only applicable in India, right? So what it can also do is like any outside IP which are outside the country or any such things, it can directly block, so that any malicious robocalls which are coming, any hacker who is trying to make our servers down from outside the country, this firewall can directly block all of those, because it can detect the IP ranges and we are only supporting our business in specific region. So all of the other IPs from where we are getting these malicious requests will be blocked directly. They won't even reach our servers, so it would avoid any DDoS kind of attack, right? So such kind of functionality firewall can provide. Now after firewall, let's talk about the next thing, which is the gateway. Okay, now your gateway can be of two types. One can be at the network layer and other can be at the application layer. So at network level it would be L3 gateway, whereas on application level it will be L7 gateway. We will discuss a bit more about it later in this video, but for now let's try to understand what's the responsibility of gateway. So when we talk about the L7 level, that is the application layer, it has three major responsibilities. First is the auth check. Say for example, this was the path, right? api.myecommerce.com and then /products. So you want that only logged in authentic user should be able to reach or access this. Okay, so how can you do that? You can't always go to the authentication service because there will be millions of requests in a big system. Like you have multiple microservices, one can be related to products, one can be related to like orders, one can be related to the profile, and many more, like making a transaction, all such things. So your system can be really big and there can be multiple microservices. So in case for each of the requests, if you go to the authentication microservice to validate if the user is valid and authentic, it won't make any sense because then your auth service will get a lot of load and it won't scale. So gateway helps us with that problem. For anything, of course, for login and sign up kind of flows, you need to go to the authentication service. But apart from that, just to validate the user, authenticate the user, the gateway can do that part. So basically gateway validates the JWT token. What is JWT token? It's JSON Web Token. It's kind of a self-sufficient token based on which you can validate or authenticate the user. Now the complete authentication flow containing the JWT token, how the auth service works, how other microservices validate all this part, how gateway validates this token. So all that information, that's a like complete big video. So all that part I can explain that in a separate video, so that we are currently able to discuss how API works, and the authentication flow will take that in a separate video. Okay, just put in the comment section if you want to know how authentication flow works, what is JWT and all such information, right? So but here the main point is, one of the responsibility of gateway is to the authentication checks. So for example, we are talking about the products. So before going to the products microservice, we need to make sure that the user is valid and user is authenticated. So that work will be done by gateway. Apart from auth check, another major responsibility of gateway is rate limiting. What is rate limiting? Say for example, you have kept like for a client, there are maximum 1000 requests allowed per second. Okay, so in this case, if from a client you get more than 1000 requests, all those requests after 1000 will be basically rejected. And who rejects that? Gateway rejects that, and it gives you the status code 429, which means too many requests. If you want to learn more on the status code, what is status code and what does it represent, you can refer to this video. Now you may ask, like, why is this rate limiting required? So one of the case can be DDoS attack. So any malicious user or hacker or robo attacks, they can try to make your server down. So they can make a lot of requests every second or minute, which will put a lot of load on your servers. And in order to avoid all such kind of DDoS attacks, we put rate limiting, and we put that on the gateway level. So API gateway will handle it so that the load does not come to the server. So if threshold is reached for any client, if more than 1000 requests are coming, those will be automatically blocked or rejected by the API gateway, and those even won't reach to our servers, and hence the server will not get that load, right? So in this way, the API gateway is saving the complete system from the DDoS kind of attacks. Okay, so apart from auth check and the rate limiting, third major responsibility of gateway is routing. Now what does that mean? So as you know, if your system is quite big, like if you're designing something like Instagram, YouTube, WhatsApp, Netflix, or any such big system, there will be multiple microservices. Say for example, another microservice to handle the orders of the user, another microservice can be the profile of the user, another can be related to the transactions, and many more. Like based on your system, there can be many of those microservices. Now as we discussed, the main host part will remain same most of the times, right? For example, you have amazon.com, and after that you generally have the product information or the orders or profile, all such thing can happen. Like for example, you can see here it talks about the products one. So now if the API request is for the products, it should go to the products microservice, right? But how will it go? Like some system or component should be there which should be able to route this request to the correct microservice. So API gateway is that system. Okay, so whenever it sees, say for example, products in the path, okay, so what it will do is route that request to products microservice. And in another case, if it sees orders in the path, so what it will do is like route that request to orders microservice. Similarly for other microservices also, based on whatever path is there, it will route that to particular microservice, because that microservice will have the logic what needs to be done for that request, right? So you can see here three major responsibilities of API gateway. That's why I said whenever you are giving system design interview rounds of high level design, generally you mention gateway, okay, and with that you mention these three basic responsibilities of gateway. It will do auth check, it will check for rate limiting, and it will route the request to the correct microservice. So you can think as like it intercepts and then forwards the request to the correct backend microservice only if the check passes, right? It is checking for authentication and it is checking for rate limiting. In case both of these pass, then it will basically forward it to the correct microservice based on the path. Okay, we will talk more on gateway, but before that let's go to the third component, which is the load balancer. We already talked about firewall and the gateway. Now let's also talk about the load balancer. So let me explain it to you in this way. We said like API gateway will forward the request to the correct microservice. Say for example, this is your products microservice and this is your orders microservice, right? And we said like from the API gateway it will go to the products microservice in case the path contains products. But now as we already know that every system is distributed system, what that means is like products microservice will have multiple servers. It won't have like single server, because single server or single computer will act as a single point of failure. Just in case one of the machine is not working, then the complete system of products microservice will fall down, right? We don't want that. In system design, we always want distributed system, which means there will be multiple servers when we talk about products microservice, right? So API gateway is simply forwarding to the products microservice. But now which server in this products microservice to pick? Say for example, I'm just showing like 5 machines are there, can be many, right? But just for an example, you can say there are 5 machines for this products microservice, right? So now on which machine this request should go? That's the main question. And which component will take care of that part? It can't happen like automatically it will go to some particular server, right? There should be some component which should handle like this request is going to this one, all such things. Because if we don't do that, say for example all of the requests are going to the first server, then this particular server will get overloaded like crazy, right? And rest of the servers are underutilized, they are not getting used, so this server will basically crash because it will get a lot of load. So we don't want that. What we want is like all the servers get like equivalent kind of load, so the load should be distributed among the servers. So that work is done by the load balancer, so it will distribute the request across multiple servers. Okay, again as we said, like the gateway works on both the network level and the application level. Similarly, so load balancer also works on the transport and the application level. That's why we are saying like L4 and L7. This is same as like the image that I displayed to you earlier. This image you can clearly see the L3 level is the network, L4 is transport, L7 is the application layer. Okay, so basically your firewall works on these L3 and L4 level. The gateway can work on 2 levels. The the L3 level and L7 level, and load balancer also works on two levels. One you can say as the L4 level, which is the transport layer, and then the application layer. Now how does the load balancer decide to which server request should go on? So there are multiple techniques, algorithms you can say, such as round robin is there, least connections is there. Least connections you can simply understand like whichever server has the least kind of load, it will give that request to that particular server. Round robin is like you can say one by one the load will be sent, like first request come to here, then second, then third, then fourth, then fifth, then sixth again comes to the first server. So this is kind of one of the technique in which you can distribute the load. Then there is also weighted routing, which means like you also check the load on the current server. If a server is overloaded for now, you don't put that new request to that server. Instead of that, you give it to some other server. So like that, there are multiple techniques which are involved. So hashing is there, and very famous one, consistent hashing, is one of the techniques which is very widely used and which is very famous, right? So we won't cover consistent hashing in this video because again we will deviate from the main topic of our how API works. But just in case you want to know about consistent hashing and more on the load balancer, how and what techniques does it use, put that in comment section. I'll create a separate video for that part. Okay, so the main responsibility you can clearly see of the load balancer is that to distribute the load among the active servers, okay, so that none of the server gets overloaded, because in case you are overloading a server too much, then it will crash. So you don't want that. That's why we have the load balancer. So clearly at this step you can see load balancer doesn't care about the authentication. It just tries to balance out the load between the healthy backend servers, right? So authentication part we already took care in the API gateway. That's why we have separate components, like firewall is there, gateway is there, and then load balancer is there. So load balancer, as I mentioned already, there can be two types, L4 and L7. L4 basically load balancer, it works at the transport layer, like TCP we discussed, right, one of the protocols. And at that L4 level you can also have UDP protocol. So basically at that L4 level transport layer, L4 load balancer can be present. And what's the responsibility of the load balancer at that time? So basically at the transport layer you generally play with the IP addresses, because it's kind of network and transport layer, right? So the responsibility of L4 load balancer would be to route the request based on the IP address or the port. Based on that it will route the request. Whereas for the L7 load balancer, because it's at the application level, so it does the routing based on the URLs, headers, like just I displayed it to you, the path present in the URL, and then the headers which are present in the request, right? So based on all those things, L7 load balancer will take care of, as it is working on the application level. So when you reach to the application level, you have all such information like the complete URL which contains the path and the headers which are part of the request. Whereas when you are talking about the L4 level, it's just like the network and the transport layer. At that time you only have an information of the IP addresses. So based on the IP addresses and the ports, it will do the redirection at L4. Whereas L7, based on the URLs, headers, it will do the routing. Okay, so some of the roles of the load balancer, as we already discussed, it will distribute the request across many backend servers. By many backend servers, because the system design, we basically work as the distributed system, so that there can be multiple servers when we even talk about a microservice, right? So that's why you need to know which server we are routing the request to. So that work is done by the load balancer. Apart from that, it will also maintain the health checks of the server. So just in case one of the server is dead, it makes sure that it is not routing the request to the dead server, right? Only to the active servers the request should go. Otherwise, what's the point? If the server is not working, if you are routing the request to that server, user won't get the response, and you don't want that kind of bad experience for the user. So what you want is like you always give the request to the active server. And how do you get to know whether a server is active or not? That's a responsibility of the load balancer. So it keeps on checking using the heartbeat mechanism that which server is active and which is not working, right? Another responsibility of load balancer is that just in case one of the server crashes, it redirects the request to other server. Okay, so basically you can imagine when we talk about horizontal scaling where we have multiple machines. So one main problem comes is like, now that you have multiple machines, to which machine the request should go, and that is handled by the load balancer. So via load balancer you are able to handle this horizontal scaling, right? So these were the three components: firewall, gateway, load balancer. Now when I studied about this for the first time, there was some confusion in mind, like what is the difference between the gateway and the load balancer. So let's clear that out in case you also have such kind of doubt in your mind. So basically gateway is kind of a system that connects two different networks. Okay, like for example, the network gateway which we talk about at the L3 layer, right? It connects the external internet with the internal private networks, like for example NAT. Now what does this mean? It's a very beautiful statement. Let me explain it to you in like easy way. Now let's say this is the client. Okay, so it would require some public IP address to reach to a point, right? So that public IP would be of the API gateway, you can imagine. Okay, firewall or gateway you can say. Okay, so this is a place till where you have the public IP which is publicly accessible. From outside anyone can reach to this point. But the important part is, after this you have things like your microservices. Okay, so say this is your products microservice, this is your orders microservice. So a very important point to understand here is that the client never interacts with the microservice directly. So what does that mean? It means like client can't directly go to the products microservice. No, this is not allowed. Why? Because if we allow that kind of stuff, then our system, complete system, can be at huge risk, because anyone put a lot of load on our microservice, and our microservice has to do a lot of things. It needs to check the authentication every time, because every time the request comes from outside, it needs to check for authentication and many other things, rate limiting and also stuff. And apart from that also, it's kind of a security leakage that you are providing access to your internal kind of code directly to the outside environment. So we don't want to do that. So what we do then is like all of these servers which are present in these microservices. So for example, when we talk about the product microservice, it will have multiple servers, multiple machines. Why? Because we want distributed system, right? Similarly for orders, we will have multiple machines. So these have IP addresses, right? Like each of the machine, you when you talk about these, they have IP address, because internet works on IP address, right? So these IP addresses of these machines, each of the machine in the microservice, these will be private IP address. Understand this point. These will be private IP address. So from outside you can't directly reach to these private IP address. You can only reach to the public IP address which we give of the firewall, or you can say the gateway. Okay, now after this you are routing the request to the private IP address. So gateway, the network gateway, is basically connecting the external internet. You can see here, this is the external environment to the internal private networks, right? These have private IP addresses. This is kind of complete private network. Okay, so the network gateway is handling that part, right? Someone has to do that part. Like you are having the external internet, public IPs, and then you have the internal, your private network with private IPs. So someone needs to connect that. So that part is done by the network level gateway, which is, you can say, as L3 gateway. And then the L7 gateway, which is the API level gateway, as I mentioned you already, it has three major responsibilities: checks for auth, rate limiting, and routing, right? So how will you perform routing and rate limiting? You can basically enforce policies in the gateway. So gateway is capable to have the policies based on which it will do its functionality, right? So that's why gateway is a very important part of system design, and that's why I said whenever you are talking about any big system, like we are designing Netflix, YouTube, Instagram, WhatsApp, whatever, we generally include gateway in that part because it will simplify your complete design. It is going to take care of a lot of things like security, authentication, rate limiting, throttling, request routing, and also about the protocol translation. Now what does that mean? So basically it's also a very good important point to note. We won't discuss in very much detail in this video for this part, but you should know, like for example, we have HTTP REST APIs, and then we also have WebSocket kind of connection, where the server can also give information to the client without client asking to the server. So for example, you have WhatsApp, right? So one model is like client sends the request to the server and then server gives response to the client, right? This is one your REST kind of API structure. This works for most of the scenarios, but just imagine a message application like WhatsApp. You can't live with this kind of model because if you're doing this, then client have to check for messages every few seconds or so. But we want the message kind of experience to be real time. So for that we have WebSocket kind of connections, okay, where the server can basically provide information to the client directly without client asking or for the request. Okay, we are not going in very much detail of that part, but what the major point is, like maybe the client is connected to the, you can say, gateway with particular protocol like WebSocket. Okay, why? Because we want in the chat application server is able to notify or tell the client directly without client needing to send their multiple requests. So we are using WebSocket protocol. Just imagine we are using one kind of protocol, but that does not mean that the gateway or the will interact with the internal microservices or internal network will also follow the same WebSocket protocol. It depends, like in internally we might be using some REST protocol or some other protocol. Just imagine if you are not able to understand WebSocket and REST, all such things, just imagine this is protocol number 1 and protocol number 2. So if client is connected to gateway with protocol number 1, there is no such rule that internally also you need to follow same protocol. Okay, so you can be using a separate protocol internally in the private network. So that is also one of the roles of gateways, that it can do protocol translation. So one here, two here, it's okay because we have gateway. So you can imagine, like, gateway is such an amazing thing. It is doing a lot of tasks for you. So here we were talking about gateway versus load balancer. So you can see gateway, we talked about a lot of things. Load balancer is like, it is not taking care of all such things like different networks or the routing or the auth, rate limiting, and all such things, protocol translation. Load balancer doesn't care about this. Load balancer is simply trying to balance the load between multiple servers. So because we have distributed system, there are many servers. Okay, so you just need to know to which of the server the request should go to. That work is handled by load balancer. So completely different roles. That's why we need separate components of gateway and load balancer. So basically, if we talk about the three components that we talked about, the firewall is there, then the gateway is there, and the third one would be the load balancer, right? Three components. Firewall, it basically blocks the bad traffic at the early stage so that your complete infra like gateway, load balancers, servers, database are not impacted by the bad kind of traffic. It can simply restrict that or block that kind of bad traffic in the earliest kind of stage. Okay, then comes the gateway role. You saw like lot of responsibility for gateway at network level. It takes care of about the network transition from the public internet connection versus the internal network, right? Then at the API gateway level, the L7 gateway we talked about, it works for the authentication, rate limiting, and routing the request to the correct microservice, right? And then the load balancer comes when we talk about at the application layer. L7 load balancer, now gateway has already provided you which microservice we need to work on. So but as per the request path, we have already assigned a microservice, but in a microservice there can be many machines, and which machine should handle that request, load balancer will handle that part. One thing might confuse you, like in gateway we talked about, like it will do the authentication, right? It won't go to the auth service every time. It will just check it based on the JWT, that is the JSON web token, which is self-sufficient kind of stuff based on which you can validate and do the authentication of the user. But don't worry much about that part. Just currently remember that based on the JWT token, gateway is able to do the authentication. I'll create a separate video on complete authentication and JWT token so that you get more clarity on that part. But for now, just imagine or take it as that gateway has this kind of responsibility of validating the user or doing the authentication based on the JWT token. Okay. Now, when I was learning these topics, like what are firewall, gateway, load balancer, I had question like this, like what is a firewall? Like is it a server or what kind of thing is it? Because we understand a client as a like mobile having the application, or your laptop having the browser. Servers, as I already told you, you can imagine it as a computer which has a code written, so there will be multiple computers. But like what about these things, firewall, gateway, load balancer, what are these things, right? So are these servers or what? So these are not exactly application servers, but they are kind of network appliances, but these can be hardware as well as the software. Okay, firewall can be hardware like Cisco ASA, Palo Alto, or it can also be software managed like AWS security groups, Cloudflare, all such things. So it can be both hardware or the software, but you would say it as a network appliance. Okay, then gateway, it is usually software service, like Nginx is very famous, you might have heard about it. Then AWS API gateway is there. Load balancer can also be both hardware or software level. When we talk about the hardware level, F5, Citrix NetScaler, these are the examples of the hardware load balancer. When we talk about the software level, these are cloud managed, like AWS ELB is there, GCP load balancer, Nginx again, very famous one. So basically you can imagine like these gateway, load balancer, firewall, these are kind of network appliances. You won't say those as application servers because these are network appliances. As I also told you, we have levels, layers, right? Application layer is at the most top, L7 level. Network layer comes at L3. Transport comes at L4, right? So yeah, these can be hardware as well. When we talk about the software on the cloud, as I mentioned, these are basically the service you provision and pay for. Okay, say for example AWS or Nginx is providing you some service, you basically use those services as these are on cloud, and you pay for that. Okay, so yeah, basically both options, the either you can buy some expensive hardwares for like firewall or load balancer, or you can basically use the cloud services or at the software level. By this you can get some understanding what are these components. Now another question can come is like who pays for it, like who does the setup. So basically, as I told you, these can be both like at the hardware level or the on cloud software level. You can say if you are taking the cloud services like AWS, Azure, then you basically pay for as much you use for that part. Apart from that, when we talk about the hardware elements, the yes, company also buys and manages firewall appliances and load balancers. So So you buy those kind of hardware devices as well, right? But yeah, as a developer, you don't get these for free automatically, right? Either you or your DevOps or the infra team set them up and pay for them. Like if you are purchasing them as an hardware, of course the company will purchase it. If you're using it as a cloud kind of platform service, then as much you use, you need to pay according to that. Okay, someone needs to do that setup, so either you as a developer will do, or DevOps team or the infra team will do the payments accordingly. So mostly you will see a lot of cloud getting used, like cloud services will be used more often. As you know, the cloud computing is like in huge demand, and that makes things easier. But of course you need to pay for it as much as you use. So monthly billing, yearly billing, all such things can happen. All right, so I'll come to our diagram actually, which we started for client and servers, and I'll show you all the components mentioned here. So this is our client, okay, and this is our server, and this is the database with which the server is connected to. Now in very beginning we started with simply we have the client, we have the server, we have the database, so request response, right? But we have come to this stage now where we understand first DNS component comes into picture. Why? Because you will have the URL, but the internet understands the language of IP address, and that will be handled by the DNS. DNS is the phone book of internet. It will provide you the IP address corresponding to the host. Okay, now after this, as we discussed, there will be other things involved, like TCP would be there and TLS would be also there. TCP protocol that we talked about, like how data will move in packets in TCP only, and TLS provides you the HTTPS support, using which your the complete request will be encrypted, and that's why it makes it more secure. And after that, these three components that we discussed come into picture: firewall, gateway, load balancer. Like the work of firewall will be basically to block any bad traffic at the earliest kind of stage, so that it doesn't even enter your basic infra, okay, of servers, database, load balancer, gateway. So it's kind of very initial step to block the things at the network level only, based on the IP address or the port. It works on the network layer, you can say L3 or L4. Then comes your gateway. Gateway can be of two types. It can be the L3 level or the L7 level. Okay, the role of L3 or the network gateway would be like you would have the external public internet, and then internally you have some network which is private, right? So the network gateway is acting as like, which is doing the conversion of this public external internet with the internal private IPs or the network it is connecting to that part. When we talk about the L7 gateway, three major responsibility, like we talked about: authentication using the JWT token, rate limiting, and then the routing based on the path to the correct microservice, right? So that all work is done by the gateway L3 and L7, as we discussed. The three things that I just said were related to the application level gateway L7. And then the next component, load balancer. Now load balancer can also be of two types: L4 level, which works on the transport layer, which basically routes the request based on the IP address or the port, because at the transport and the network level you generally play with the IP addresses and the port. And then you also have the L7 load balancer, which is basically working on the application layer, which basically based on the your headers and your URL path parameters, it assigns the request to particular server in this distributed microservice architecture. Okay, because gateway L7 will tell you like is responsible for this request, but then in that microservice also you will have multiple servers, multiple machines, to which server we should assign that request. It is handled by the L7 load balancer. Okay, and then comes into picture your server and database. Now I'll tell you one very nice thing here. Okay, we talked about like first step is DNS, and it will provide you IP address of the host. right? Now the important point to understand here is it will generally provide you the IP address of, you can say, gateway or firewall level, you can say, but I'll simply say gateway. Okay, so this is your client, this comes in between your DNS. So DNS will provide you the IP address, but what is this IP address of which component? This is not the IP address of the microservice. Okay, this is not the IP address of the server, because as I told you earlier also, client never interacts directly with the server. It always happens with the component like gateway. Okay, so generally your gateway or load balancer or firewall, based on the like what is the scale of your system, you will have these components. I'll talk about that. Do you always require all three of these? We'll talk about that, but just imagine for now we have this gateway. Okay, so it will have kind of public IP address. So I'm writing PU and then IP. Okay, so basically it has public IP address, but your microservices, any microservice, these will have the private. So I'm writing PR. Okay, so these have like private IP address, so client cannot interact directly with these microservices. So DNS will generally provide you the IP address of the gateway. Okay, so whenever you are making like a API call based on the host, DNS will provide you the IP address, which is the public IP address of the gateway. So you will reach to gateway, and now based on whatever things are present, like whether it is authenticated user, rate limiting is fine, after that it will do the routing in the private internal network. Okay, so it will send the request, say for example, to this microservice which is having the private kind of IP addresses, so client does not reach directly to here. DNS will provide you the IP address, public IP address of the gateway, and then gateway forwards the request to the microservice, and then load balancer of course will assign it to particular server which will have IP address which will be private IP address, right? And when the information also goes back, it goes the same way it came. So say for example it came like client, and from DNS it provided you the gateway, and then some particular microservice, it went to some particular microservice, right? So when the response come, it also comes in the same way, so the client will get response from the same place where it sent the request. Okay, so client is not directly interacting with the microservice, it is generally happening with the layers like gateway, firewall or load balancer. Right, now coming to that part, like do you always need all of these three components? It depends. Like if you have a very small kind of setup, of course, like if you have only one server then there is no point, right? If you are just like doing a very small kind of development kind of a setup, then of course you can have a simple machine and then doing all those things. But in case as you scale, you would require these components. For example, say you have now multiple machines. Okay, you are doing horizontal scaling, then of course you need the load balancer. Otherwise how would you select which machine should get this request? So for that you need load balancer. But if you have only like one microservice and very small kind of setup but multiple machine, only load balancer can be fine. You don't, maybe at that step you don't require gateway because you have only one microservice, so routing funda is already gone, and your other stuff is so small that not thinking on security in that scale. You may not require authentication at that scale, so your microservice can handle the basic things. So if you're at low scale, yeah, firewall and gateway can be removed at that. But of course as you grow, right, if you have now multiple microservices, each microservice needs to have that authentication kind of thing already sorted. At that point you need the gateway because it will route to particular microservice, and it will also take care of the authentication. It will also take care of the rate limiting so that it saves you from the DDoS attacks, because now you have big system and you need to take care of the security kind of things so that your system doesn't become down by just like simple attacks, right? Like DDoS attack anyone is doing and your system is down. What will customers say? Like, you're not doing well, right? So at that point you need the gateway. And then at the top layer, if your business is at like big level, then of course firewall is also required. Like you can block some of the IPs at the beginning level. So these kind of things, like it depends like what is the scale and what kind of business level you are, and based on that things will happen. But keeping things in short, I think when we are talking in terms of the interview of a high level design, we would always have these components: load balancer and gateway. I think load balancer still is quite understood. Many a times you don't even mention, because we already know, because it's a distributed system, so load balancer would be there. But gateway, I have seen like most of the times when you are making the like high level diagram, you generally include the gateway, because it is taking care of a lot of things. It is taking care of your authentication, it is taking care of rate limiting, which is very important, and then routing to the particular microservice. So generally we include. So it's good that you know about all these components: firewall, gateway, load balancer. These two are very important. Yeah, so I think you should know about it. Now I understand that you may have many doubts, like for example, what is the difference between L3 gateway versus L7 gateway, similarly L4 load balancer versus L7 load balancer, and many other questions. So let's discuss a brief about it, and then I'll also cover some of the doubts that I had in my mind when I learned all these topics, right? So just in case you have some other doubt, feel free to put that in the comment section and I'll try to help you out with that. Okay, so let's start first with like what is the difference between L3 gateway and L7 gateway. So as you can clearly see in this diagram, OSI layer, L3 means the network layer, whereas L7 means the application layer, right? So L3 gateway works on the network layer, whereas L7 gateway works on the application layer. So let me now put this image on side. Okay, and then we'll talk about the few other differences. Because now L3 gateway is at network level, it can only inspect on the basis of mainly IP addresses, whereas when we talk about the application level L7 gateway, it has full application context. For example, the URLs, headers, payloads, everything which are part of the request. So it can use all that information because it's at the application level, and then based on that it can perform its task. Now we know that one of the responsibility of gateway is do the routing. So we will also talk about on what basis the gateway is doing the routing. So L3 gateway, it has access to IP address, right? So based on IP source and destination, it will do the routing. Whereas L7 gateway, it's on the application layer, it has full context, so it does the routing on the basis of content. For example, what is the path, host, query params, all of these things, because it has all those details as it is working on the application level. Now talking about some of the features for L3 gateway, we talked about NAT, that is like it has to work with the external internet public IPs and then connect it with the private network or the IP addresses, right? So it will do all the conversion or transition, you can say, between the public and the private network. Whereas for L7 gateway, three major things: rate limiting, auth, and routing the request to correct microservice. Now talking about the complexity, so most of the time L3 gateway at the network level would be more of a hardware device, whereas L7 gateway, it will be more like software defined. Hence L3, you can say it will be more simple, whereas L7 can become bit complex. Okay. Some of the examples of L3 gateway are the Cisco routers, Linux IP forwarding, whereas for L7 gateway, we have AWS API gateway, Nginx, and much more. So this was basically the difference between L3 gateway and L7 gateway. Now let's also discuss about the differences between the L4 load balancer and L7 load balancer. So again, if we talk on the OSI layer, So L4 load balancer works on the transport layer, whereas the L7 load balancer works on the application layer. Hence, the L4 load balancer will inspect based on the IP address, ports, and the basic headers. Whereas the L7 load balancer, as it is working on the application level, it has complete application content. So it will inspect based on HTTP headers, URLs, payloads, all such things. So the routing basis will be also similar. For L4 load balancer, it will be connection based. It will do, for example, round robin approach on the ports. Whereas for L7 load balancer, it is content based, like based on the path, users, it can distribute the load to the server. So in L7 load balancer, you will hear out the techniques like consistent hashing, which is very famous, but that doesn't apply at the L4 level. So this was mostly on L4 and L7 load balancer. Now let's move forward. So basically the flow, you can say, as we discussed. So firstly you will have the client which will make the request, but because internet understands the language of IP address, and so hence there comes the DNS, which would be the first component, right? Here comes the DNS, which will provide the IP address. Okay, IP address it will provide you, and then there are other things as well, which was like the TCP, and there is also like TLS, which will provide you the HTTPS support, right? These protocols will be used, basically the packets are sent via TCP only. Okay, and TLS will provide you that encryption, the security part, which HTTPS will provide you. Okay, so the DNS will provide you the public IP address, which is generally of the firewall or the gateway, right? The whatever is your first layer in the infra. So if we are having the firewall here, so this IP address that we will get from the DNS, it will be of the firewall. So the flow will be it goes to the firewall, which does the very basic level of checking of things. It can block the request which is having any malformed headers, which is part of the blacklisted kind of IP ranges. So it will simply block all those things so that bad request doesn't enter that your infra. Okay, and then basically you have your next level as the L3 level gateway, and then after that you have L4 load balancer, and then L7 gateway, then L7 load balancer, and then finally your microservice. So just in case you are finding it difficult to understand between L3 gateway, L7 gateway, L4 load balancer, L7 load balancer, you can simplify the design something like this. You have client, you have DNS, TCP, TLS is there, then firewall comes, then gateway comes, then the load balancer will come. Okay, you don't need to specify like L3, L4, L7, L7. Simply put firewall, gateway, load balancer, and then your microservice. Okay, and of course it will be connected to a database, so I'm writing database as D here. So in short, you can summarize like this: client, DNS, TCP, TLS, firewall, gateway, load balancer, microservice, and your database. But if you know in detail about L3 gateway, L4 load balancer, L7 gateway, L7 load balancer, it's the best thing. But this is also great, right? But this is basically the generic flow that I wanted to tell you. As we already discussed, DNS will provide you the public IP address, which would be of your first kind of layer in the infra. Any of these it can be. Most of the times if you don't have firewall, it will be of the gateway. Okay, so it will provide you the IP address of the gateway. So client never interacts directly with the microservice, right? It always connects via the gateway, right? Okay, so next question that may come in your mind is like, we mentioned that gateway will route the request to the correct microservice, right? So based on, say for example, path, it will define to which microservice the request should go. But the question comes like, how does it do that? How does the L7 gateway redirect or route the request to the correct microservice? Very wonderful question, right? So the answer is, as I told you earlier, the gateway has the capability of configuring the policies. So you can configure the policies in it based on which it can perform the operation. So L7 gateway, it uses declarative routing rules and service discovery to forward the request to the right microservice. Now in technical terms, you should not use redirect. When we are saying from gateway to the microservice, we should not say it is redirecting the request, because in technical term of backend, redirect is used for 3xx status code. You can refer to this video if you want to learn more about it, like what is a status code and what does 3xx mean. So you might have seen the tiny URL system design question in which redirection happens from the short URL to the long URL. In that, we basically send the status code of 3xx. So that is redirect in technical terms of backend development, you can say. So we should not say the L7 gateway redirects the request. We should say it is doing the internal proxying, or it is forwarding to the correct microservice. Okay, now this is fine, but like how does the L7 gateway is doing this internal proxying or forwarding? Let's discuss about that part. So basically, as I said earlier, you can configure things like policies to the L7 gateway, so it will have its routing rules or the plugins. You can basically configure it via YAML or JSON files. Okay, so it can have the route matching. For example, you can see the regex here. We have mentioned like v1 users, and after that we have put like star. So anything after v1 slash user slash anything is present, it will pick that. Okay, so we can define other things in it as well, like what is the host, headers or methods, what can be the cases. Similarly, for the query params, we can define all such things. One of the simple example rule can be if the path starts with v1 slash users, you send it to the user microservice. Now for these routes, we can define the target as well. For example, static, that is the fixed IP addresses or ports. Like we can mention all that target. Similarly, we can also have the dynamic service discovery integration with Kubernetes and other things like the console DNS. Okay, so basically you can define the route and then the targets corresponding to that route. So let's see an example so that you get more clarity on that. So for example, the client hits the gateway with this API post v1 users. Okay, it will contain the JWT token, and we already discussed that to authenticate the user is one of the responsibility of the L7 gateway using the JWT token. Now we have not discussed JWT token and the authentication flow in complete detail. I'll put that in the separate video for you. So the first step would be it will check the authentication using the JWT token, and also it will check for the rate limiting. In case any of these fails, it will reject the request as invalid. So this is the work of L7 gateway, right? So another responsibility major of gateway is to do the route matching, correct? So it will basically scan the rules based on the priority orders. So just taking an example here, as we said, like v1 slash users, so it will match it to the user service. In case it does not find anything, it can return 404, that is not found. So once we have a route, what it can do is like it can fetch the targets for the user service, because our route is to the user service. Now we talked about it, right? It can have kind of static fixed IP addresses, you can define those, but it can also have like dynamic kind of working, where it can fetch the things with the integration to the service discovery, right? So here we are taking an example of that dynamic part. So it will fetch the targets for the user service from, like we can use Kubernetes or console, and based on that it will return you the IP addresses. Now how does this happen? Basically the gateway will query the registry, whatever we have made, like for the dynamic one, Kubernetes or the console or anything for the service endpoints. Then it will resolve the user service, because we are talking about the user service specific here. Based on the path routing we define that, so it will resolve it to the list of IP addresses or the ports. Now it can be done via the API calls or DNS SRV records, anything like that. Then basically it will also cache the result so that it can be quite quick, and we can also define like TTL for the cache, like which will means the expiry of the cache we can set. So in this way it will have the IP addresses, that is the targets for the route. Okay, now once you have your targets, then the role of load balancer comes. It will use the techniques like consistent hashing so that it can pick one of the servers. Like for example, in this case we had like 10.0.4.1 as one, and another server was like 10.0.402, and after that there was port, right? So based on consistent hashing, say for example, say it picks like 10.0.4.1. okay, so it picks this one, so the request will go to this particular server in the user microservice. So in this way basically the routing is done using the gateway, and then it is given to the load balancer to select the particular target in the list of targets that we already have corresponding to the route, which is your selected microservice, right? Okay, so let's move to the next question, which is like how basically the responses are sent back to the client. Like for example, we understood like the incoming flow is from like the client, it goes to the DNS to find out the IP address, then firewall, gateway, and then load balancer, and then it goes to the microservice, right? So we understood that the request doesn't come directly to the microservice from the client, right? It happens using the help of firewall, gateway, load balancer, right? In similar way, when we talk about the response is also not sent directly from the microservice to the client. So they follow the reverse path of this. Like this is the path which was followed for the request. The reverse path will be followed for the response. So the microservice won't send the response directly to the client. It won't happen. Okay, just in the same way the response will go in the reverse order to the client. So this thing ensures there is consistency, security, logging, transformation, and centralized control. So the main part is that client remains unaware of the internal hops. So the client doesn't know that you have your firewall, you have your gateway, you have load balancer, and then basically you have your microservice. Client doesn't need to know about it, right? So client is simply making a request. So at very brute force level, if you understand, client as an end user, I have no information like how are you doing all the things, even if you have any server or not. But if we talk about your like for example your application or your browser, even that does not care if you have your load balancers, gateway, firewall, whatever. It's like they just want the response, right? So there is abstraction out there. So the client will get the response from the same thing to which it sent the request. It is not like it was sent via the gateway, but the response is coming directly from the microservice. Then it will be wrong, right? Because sent the request to someone else and came response from somewhere else. So it follows the same reverse order path to reach to the client. Okay, now you may think like why are we going via gateway or components like firewall, load balance, why we are not going directly? So there are many reasons, like we already discussed about few earlier. One important part is the security. So the gateway can filter the responses. We talked about all the things like what is the role of the firewall, what is the role of the gateway, what is the role of the load balancer. If you don't have these layers, your microservice has to do all that stuff, and in case it's not doing, it's kind of a complete security leak that can happen. Anyone can do the DDoS attack directly to your microservice then. But because of these layers, we are safe because the IP addresses of the actual servers is private, right? Only the public IP address would be of the first level. Let's say for example you have your gateway as a first layer, so that would have the public IP address. The public is so the external internet will connect to the gateway, the public IP, but after that it does the forwarding or proxying to the internal IP addresses which are not known to the external world. So these layers like firewall, gateway, load balancer, they provide you a lot of security, right? And then of course they provide you scalability. When we talk about the big systems like designing YouTube, WhatsApp, Instagram, all such things, you have lot of servers, you have lot of distributed system, you have lot of load, and you need to take care of all the security and all such things. So that will be taken care by all these components. Just imagine you have multiple servers. How will you define like which server will get the request? So you need load balancer, right? So all these components that we discussed, the gateway, load balancer, these are like very important. So you don't want the request coming directly to the microservice. Via these components, everything is well defined. You can scale the system, there is good security, the performance improves, and they provide a lot of features, right? So that's why the client won't directly interact with the microservice, right? But now one major question that came to my mind at that time was like, we said like we will use the proxying model, right? Like the way the request came, it will go in the reverse order, same way back to the client as the response. But how does that actually happen? So let's try to understand that. So basically when we talk about the proxy or the reverse proxy behavior, there are like hop by hop connections. What does that mean? So basically when we start a connection from client to say gateway, right? This is your client and this is your gateway. So there is one connection. Now it doesn't mean that the same connection will continue till the microservice. So each of the component will have a separate TCP connection. Okay, when gateway is connected to load balancer, it is a separate connection, it is not same as this connection. And when load balancer connects to the corresponding server in the microservice, this connection is a separate connection, it is not same as this one, not same as this one. Okay, each hop has a separate connection. Now because this layer like gateway to load balancer or load balancer to microservice, this is completely the internal or private kind of network, these are private IP addresses. So the external user or the client or the public internet, they don't know about these connections. Okay, so I know this seems a bit complicated, but it's in a great thing. When I understood this, like I felt really great. So let me try to explain it to you with both of the things, like the using the WebSocket connection and also the normal REST API also. Both cases we will see with an example. So let's first see an example of, say you are using a chat application. Okay, so there are two users A and B, they are sending messages to each other, you can say. So for chat application, as I told you earlier as well, we generally use like the WebSocket connection for that. We don't use the REST APIs for that part. Why? Because for the REST API flow, there is basic concept like when we talk about the client and the server. So the client will send the request to the server and server will give back response to the client. Server is giving back a response only when the client send the request to the server. Without request, server is not giving back response to the client. This is basic flow of your REST APIs, okay, which are generally used in most of the applications or website, you can say. But when we talk about the special cases like message application, so it's kind of a real-time experience that we want, right? So just in case we were using the HTTP REST API in message application, it would become so difficult. Why? Because say B sent a message to A. Now how can server send something to the client without client asking to the server? So one thing that the client can do is like keep on polling to the server, that keep on asking like, do you have a message for me, do you have a message for me, do you have a message for me? You can clearly see it is not a great thing, because then like each of the client will keep on asking to the server, and a lot of time there is nothing, no message, but it will still keep on maintaining the connections then creating new connections, closing the old ones. So it is a lot of you can say effort, and it may not provide you the real-time experience in case you are putting a delay to the calls, right? So that's why we have the WebSocket kind of connection, which is a protocol you can say, where the server can give information to the client without client asking for it. Okay, there is a kind of a duplex connection, like two-way connection. So if you have heard about WebSocket for the first time, don't worry, don't confuse it too much. I can create a separate video where I can talk about like the REST APIs versus the WebSocket, but here I'm just talking about that example so that you can get some clarity. So say there is a message from one of the client like hello, it will go to the say firewall, and then it will go to the gateway, and then it will go to the load balancer, and then it will go to the microservice. And when it has to send the response back, it will follow the same path back again. Okay, but the main point here is like for each of the component, when we are moving to the next component, we create a new connection here. So this connection is not same as this one, this is not same as this one, this is not same as this one. So for every hop we are creating a new connection, and it goes back in the same way. We had this connection, so on this connection only this will go back. Now this had connection with this using this, and it goes back in the same way. Okay, similarly for this. So that is the main point. Every hop connected, it has a separate connection. Now I understand that it may have become quite complicated for you, so let's take an example, and I promise with these examples that we are going to cover, you will get a great understanding of how the flow completely works. Okay, so let's see an example. So in this example we are taking one component as client, so I am writing C, which is representing client, and then after that I am using here a gateway. Okay, so I'm not taking other components like the firewall, load balancer in this. We are just concentrating on client, gateway, and then the microservice. Okay, so I am writing here M, client, gateway, microservice, right? Because your components like firewall, load balancer, they depend on your setup, what kind of business you have, how big or small. So in order to keep things simple here, we are just focusing on client, gateway, and the microservice. After this we will see one more example where we will include load balancer as well, so that you get more clarity, but we will begin with this one so that things remain easy to understand and clear in the beginning. Okay, so each of these will have IP address. Say for example, when we're talking about the client, this is the IP address and this is the port. So you can see this is IPv4 address, right? And similarly the gateway, it also has this IP address and this is the port. So client gets the IP address of the gateway from the DNS. Okay, and now it will make the request to the gateway. So now what gateway will do is like when it receives the request, say we are talking about the sockets, or you can understand it like the WebSocket kind of protocol. So whenever it receives on its socket, so it assigns an ID to it. Say for example, we can say here it assigns it 42, right? This ID that we have assigned is acting as a mapping, so it basically represents from this IP we have come to this IP. Okay, so we have assigned an internal ID for it. Now as I told you, when gateway will communicate with the microservice, it will open a new connection. It won't use this connection, it will open a new connection which is different from this one. Okay, so on every hop we are creating a new connection. So when the gateway opens a new connection, it assigns a new ID for this socket. Say for example, we assigned 78 to it. Okay, so this was the internal ID of the socket where gateway received the request from the client, and this is the ID that we have assigned from where we have created a new connection through which we will send the request to microservice. Okay, now before going ahead, what it will do is like it will map 78 with 42. Why? Because when coming back, we will follow the reverse proxy. So same path we have to come back. So if it has the mapping like 78 is connected to 42, using that particular mapping, it can send back the data to the client. Hence, it will do the linking like 78 is connected to 42. Now when the microservice receives this request from the gateway, it will also assign an internal ID to that connection. Okay, and now once the microservice has completed the processing, it will send back the data on the same connection. So the gateway will also receive that information, the response on ID 78, the same ID from which it sent the data to the microservice. Now further, gateway will check the mapping of this internal ID like 78 to which ID was it connected, and we know that 78 was connected to 42 because we kept the mapping. So now it knows that it has to give back the response on this internal ID 42. So it is able to send back the response to the client because it has this mapping. So the client receives the response from the gateway to which it sent the request. It is not getting the response directly from the microservice. Now you can imagine, in case some other client made a request to the gateway, then that would have been assigned a separate ID. Okay, say for example it could have been like 44, right? And from gateway, when we are creating a new connection, it would have created a separate ID for this separate client, right? And their mapping would have been held. So you can clearly see in this way all the requests are independent of each other. So there is no confusion because we are maintaining the mapping at each of the component level, right? I know still you might have doubts like what's happening. So let's see one more example via which you will get a better understanding. But from this example, you can simply see each of the component has its own IP address. Whenever the component will receive the connection, it will assign an internal ID, and also when the component talks to the next component, it's create a new connection. It doesn't use the old connection which was coming from the previous component. It creates a new connection, and while creating a new connection, it assigns another new ID to it from where you are making the request, and then it will link this ID with the previous one so that you have the connection of, you can say, backend and the front end. So in this way you will contain the mapping, and whenever you are getting the response back, you will use the same mapping to get the previous ID, and based on that you can send the data back. Okay, so let's see one more example through which we'll get more clarity, right? So in this example we will include multiple components. The first component will be our client, just like the last one. Then we will have the L7 gateway, so I am writing G for that. Then here we will also have the load balancer, okay, so that you get more clarity this time. And then finally we have our microservice, so I can represent that with M, right? So now each of these components will have their separate IP address. So for example, for the client A, this is the IP address, this is the port, and it makes a GET request, get v1 users 123, and that also contains the JWT token. Now gateway also has the IP address. Now because this is the first component of our infra, this will have the public IP. You can see the public IP here. This is the public IP and this is the port. So this will handle the authentication using the JWT token. We have not talked in detail about the authentication flow and the JWT token. I'll create a separate video on that part, so don't worry on that side. Then we have the load balancer. Now because gateway had the public IP, rest all of these will have the private IPs, or you can say the internal IPs. Okay, so for load balancer we are just taking example, this is the IP, this is the port, right? And then this microservice server, it will have this IP address and this port. So each of the component has its own IP address. Now when client is making the API request, this one v1/users/123, based on the host, DNS will provide the public IP address of the gateway. So the request will come to this gateway. And now what this gateway will do, it will assign an internal ID on the socket where it receives the request. Now let me take it down where I can explain you in a better way. Okay, so this is client, gateway, load balancer, and your server in the microservice. Okay, so when gateway receives the request, it will assign an internal connection ID to it. So for example, we can say it assigns like 42 as an internal ID to this. So this ID represents the mapping, like from the IP address of the client we have reached the gateway. Okay, and this is represented by this internal ID which we have mentioned 42. Now this is L7 gateway, so it will perform its own task like authentication using the JWT token, and then rate limiting, and then basically routing. So for routing, it will check the path because it contains users. So based on the policies, whatever is configured, we can say it tells that it needs to go to the users microservice. But you know, user microservice can have multiple servers, so we require the functionality of load balancer to select a particular server in the user's microservice, right? So instead of M, let me write here S, because we want to pick specific server. Okay, in the microservice we are talking about a specific server, right? So from gateway, now we need to go to the load balancer. But as I told you, whenever you go to the new component, it creates a new connection. It doesn't use the old connection. So gateway will create a new connection to connect to load balancer, and here from where it creates a new connection, it will assign a new ID to it. So for example, here we will assign 78 as an ID to this part. Okay, now what we need to do is keep the mapping of 78 to 42, because that is how you can go back. You know that this is connected to this because you need to give back the response to the client as well, right? So you will maintain the mapping. So 78 we can just say like backend part, because going further you are going to the data layer, and 42 you can just imagine it as the front end part, because from here you will go to the front end. Okay, so you will make the mapping. So till now, like 42, it contained kind of the mapping, the client IP address to the gateway IP address, right? So we assigned 42 as an internal ID to that where we received that from the on the gateway. Now when creating a new connection from gateway to load balancer, we are assigning a new ID 78, and we map 78 with 42, and due to all these mappings you are able to send the correct response to the corresponding client. So there are no confusions in that way, right? Now when the load balancer receives this request, it assigns a particular ID to it as well. Like for example, at gateway also we assigned an ID 42 when we received the request from the client, and while creating a new connection we created a new ID. Now when receiving the request at load balancer also, this component will also assign a new ID to it. For example, we have given 99 to it. So basically when load balancer receives the request, it knows like it is coming from gateway. But you can also include something like X forwarded for the IP address of the client for the visibility, because the starting request was made by the client. So you can include that part such a way so that you have all that information at each of the level, but load balancer knows that it is coming from the gateway. Now from here load balancer will perform its task, like it can do consistent hashing or any other technique to assign a particular server in the user's microservice. And you know, when it has to contact the particular server, it will open a new connection. So this connection is not same as this one, it is not even same as this one, it's a new connection, it's a separate connection. So when the load balancer creates a separate connection, it again assigns an internal ID to that. So just take an example, we are assigning internal ID 112 to this. Now again the load balancer will maintain the mapping, it will connect 112 internal ID to 99, because through this only it knows the previous part. So just you can say 112 as the backend mapping to the front end mapping of 99. Just you can imagine as an example, but it maintains the mapping. So you can simply imagine the mapping as from where it is creating a new connection and map it to the place where you received the connection from previous component. Okay, so 112 is a place where it is creating a new connection. 99 is the internal ID showing it received the request from the previous component, that is a gateway. So it connects 112 to 99. You will understand it more when we are talking about the reverse proxy, like how the response comes back. You will get more understanding on that. But for now you can clearly see what we will do is like map 112 to 99, right? So in this way it can connect back to the gateway. Now once from load balancer you are sending the request to particular server, this server also can create a separate ID here. Okay, it will create its own ID because it is receiving a request from the previous component. Now one more thing is like server can see that request is coming from load balancer. It is not coming directly from the client, but yes, you can forward the client IP like this way, but server knows it is coming from load balancer IP. Okay, now the server will perform its task, like whatever thing it has to do. It will generate the response and it will send back the response on the same internal ID which it had. Okay, so it will send it back and the load balancer will get it back on the same ID 112. Now once the load balancer gets the response on ID 112, it checks the mapping of 112. What is 112 mapped to? And we know here it maps to 99. So 99 represents like the mapping on which socket you did received the request, right? So now from here only you will send back the response and the gateway will now receive the response on the socket ID with this internal ID 78. Again it will check the mapping. What is 78 linked to? 78 will give the mapping of 42. 42 is the internal ID which represents the socket where you received the request from the client. Okay, so it will give back the response on that same mapping. Now 42 contained this kind of mapping, right? Like this contained the IP address of gateway and the IP address of the client. So on similar way it goes back to the client. So client is getting the response from the place where it made the request. It is not making the request directly to server and it is not getting the response directly from server, right? Made the request to gateway and also getting the response back from the gateway. But you can clearly see based on this internal IDs and mapping of these internal IDs, you can basically send the data and receive the data on same sockets, right? So in this way there is no confusion and you get back the response for the corresponding client. So there is no mixing like that. So whenever there is another request, it will be assigned a separate kind of ID and separate mapping will be maintained for it, right? So basically this is the kind of thing that I explained to you. On the request side we maintain the mappings, right? And when going to the response flow, it is just reverse of the mapping lookup, right? So the microservice is sending back on the same socket on which it received the request and the load balancer will read the response on the backend socket 112 because we assigned this ID as 112. And now further it checks for mapping. 112 is linked to 99 which is the basically gateway, like it represents the socket from which you received the request from the gateway. Now basically it can add some more rules like what was the response time on this part, that goes in the header part, and basically it forwards it over internal ID 99 because we fetched the mapping of it, right? So it sends it to the gateway and basically due to this internal ID you can send it back from the IP address of the load balancer to the IP address of the gateway. So you can simply imagine all these IDs that we have given, they contain kind of these kind of mapping like the IP address of the previous component and IP address of the current component. So in this way you are sending also back in similar way, right? So once the gateway receives, it reads the response on the backend socket 78 because we assigned this from where we were creating a new connection as 78. Okay, so it reads on that socket 78, it looks for mapping. Now 78 is mapped to 42. You can clearly see here we mapped 78 and 42 because 78 is from where we made a new connection from the gateway to the next component, and 42 represents the socket ID on which gateway received the request from the previous component, that is the client, right? So in this way, like, it needs to send back on 42, right? So it forwards over 42. It can add some more information to the response, and then as 42 represents the mapping from the IP address of gateway to the client, so now client gets the response on the original socket because we had this kind of mapping. This was the client IP address, this is the gateway IP address. So now client has the response, it can parse it and display it to the user. Okay, so long story short, whenever a component talks to the next component, it creates a new connection, and each of the component assigns the id is created on two scenarios. Whenever it receives the request, okay, from any of the component on that socket, it assigns an id, and whenever it creates a new connection, you can see here 42 where it gets the request, and 78 when it is creating a new connection, and then it will map both of these. 78 is mapped to 42. Similarly, going forward also, these are all connected, and each of these id, it's kind of like symbolic of like IP address of the previous component, and based on these, basically you know the IP address the previous component and the current component, all such information you have, and this way you are also able to send it back the same way you received the request, so the same way or the reverse way you are sending the response back. Okay, so these kind of mapping, it can maintain anything you can imagine, like in memory hash table. So this is where things happen. So as we are assigning new IDs, so even if there are multiple requests, there is no ambiguity because the IDs will be different for each of the requests at each of the components, so there won't be any confusion or ambiguity according in that part, right? All right, I hope that this gave you some clarity. Now just to give you the summary of the complete thing that we did, I'll just make a diagram for you so that, and I'll also keep on telling what was the functionality of each of the component, because it's been a long video and we covered a lot of stuff. So I want that in the summary part you understand whatever we covered. Okay, so this is our first component, which is client can be like, if you're using mobile phone, so any application on the mobile phone, it can act as client, or if you are using the desktop or computer, then the browser can act as a client. Okay, so on client you generally make the request like www.google.com, then /users/123, all such kind of things, but the internet understands IP address, right? It can't understand this text names that you understand more. Like as a human, you are more comfortable with the names, saving the names or entering the names, but internet uses IP addresses. So in order to get the IP address, what we use is a DNS. So functionality of DNS we already discussed, so it will provide you the IP address. So one basic thing, of which component will it provide you the IP address? It generally provides you the public IP address, which is the first layer of your infra. It can be of the gateway, if the gateway is your first level of the infra. So it will have the public IP address. In case your system does not have gateway, it only has the load balancer, then the load balancer will have the public IP address, and DNS will return the public IP address of the load balancer. But general part, when we talk about the distributed system of system design, it does not return you IP address of the servers directly. Clients do not interact directly with the servers. There are multiple components like firewall, gateway, load balancer, and then after that you reach to your server. So all these other things will have private IP addresses. Okay, so once you get the IP address from the DNS, right, then you need to build up the connection, and in order to build up the connection, you will require the protocol, which is very famous protocol TCP. Now there are other protocols as well like UDP, but most of the time we use TCP. So three ways, like first client will send SYN to the IP address. From there you get like SYN acknowledge, and then finally from client again you send acknowledge. So three-way step, and based on that your TCP connection is built. And after that comes another step, which is the TLS connection. This is basically required to involve HTTPS, which provides you encryption. So overall you get like security, right? So these are kind of the networking layer, you can say. First DNS, then you build a connection TCP, then TLS, and based on this, once a connection is established, the client can interact or send the request on that IP address. Because the packets, like when we say request, so technically the packets flow via this TCP only, right? So say DNS provided you the IP address of the first layer. Say for example our first layer is the firewall, so here comes the firewall, right? Let me write here firewall. So what's the use of firewall? Basically it will block a few of the bad requests which has the missing headers, or you can say authentication, or say some of the important things are missing in it, or you can also imagine some of the blacklisted IP ranges. That firewall can simply block all of these requests, so that those requests don't even reach our further infra, like it doesn't even reach your gateway, load balancer, and of course your servers are safe from all such requests. So it helps you prevents like DDoS kind of attacks, where the hacker or the robocalls or the malicious users try to put so many requests on your servers to make your servers down. So firewall can help in that way, right? After this, the next thing that comes is a L3 level gateway. Okay, so let me write L3 gateway. So I told you the OSI layers. L3 layer represents the network layer. So this is generally, you can imagine as a hardware kind of setup. What's the role of this? You can imagine like from the external internet you're getting the request from the public network or the public IP addresses, but further there will be all the private networks, right? Private IP addresses, your private network. So the L3 gateway helps to do this conversion, like it handles like the public kind of or external kind of networks, and then it routes to the internal kind of networks. So that is kind of a role of a L3 gateway. Okay, and then the next component comes is the L4 load balancer. So let me write it down. L4 load balancer. Okay, so again here comes the OSI layer. The L4 layer represents the transport layer. Okay, so what's the use of L4 load balancer? And so the role of load balancer is generally to distribute the load among the multiple things, because you have the distributed system in system design, so there will be multiple machines always, multiple things always. So the load balancer will try to distribute the load across multiple things. Okay, so as the next component is the L7 gateway. So you can imagine all of these are distributed. When I say distributed, it means like there are multiple of these present at each of the levels. So let me first write it down, L7 gateway, and then I'll explain that part. So when I say L7 gateway, it doesn't mean like we have only one of that gateway. There will be always multiple gateways, because when we talk about the big systems in system design, like design YouTube, Instagram, or WhatsApp, or anything else, right? All such big systems, there is a huge load. There are lots of millions and billions of users. right? So there won't ever be only single kind of thing. So when we talk here like firewall or L3 gateway, L4 load balancer, L7 gateway, and the servers, everything is distributed. So many machines, right? So all of these are distributed. So the work of L4 load balancer is to distribute the request to the L7 gateway. So because there will be multiple L7 gateway, it will select a particular one based on the techniques, right? Because these are at the network and the transport layer. L3 layer, L4 layer represent the network and the transport layer in OSI model. So they don't have access to the complete request at this time. They generally do the processing based on the IP address or the ports, you can say. So it will select the L7 gateway based on the IP address, you can say, or the basic headers. And the generally technique used, you can say, is like hashing can be used, round robin can be used, and there are multiple techniques. But at this layer we generally don't use consistent hashing because we don't have access to the complete request till now. Okay, so you can just imagine like based on the hashing, it selects the particular gateway. Now you may have a confusion in mind, like for L7 gateway we selected the particular gateway using load balancer at L4 level, that's fine. But how about these? I said like these will also be distributed, so there will be multiple firewalls, there will be multiple L3 gateways. So how are these selected, because we don't have a load balancer out here? So the answer of that is like at this layer it is generally done using firstly by the DNS. We discuss about like the anycast technique that is used by the DNS, right? So using the DNS and the anycast technique, you can route it to the nearest present firewall and the L3 gateway. Okay, so it assigns you a particular region. Now of course at a particular region as well you can have multiple firewalls at L3 gateways. Then after that, the internet routing protocols like BGP that we discussed in this video helps to identify the particular firewall and L3 gateway. That uses of course the metrics like the shortest path, closest location, and all such things. So basically you can understand like till this layer we reach to the particular firewall L3 gateway using the network protocols. So that happens at the network layer. But after that we use the load balancer firstly to reach to a particular L7 gateway. And then further also we'll see one more use case of the load balancer at the L7 level. Okay, but before that, L7 gateway, there are three main things that it needs to do. First is like the authentication. It uses the JWT token to authenticate and validate the user. Second is the rate limiting. It keeps a check. Say for example you have kept a limit of 100 requests per user per second, or you can imagine like per minute or anything like that. So in case the saturation is breached, say you are making 110 requests, so after 100 all the requests are basically dropped. They are not sent further to the next levels and it does not reach the server. That is how you sustain. It does not allow putting so much load on the server. So rate limiting is one of the features of this. So authentication, rate limiting, and then routing, basically forwarding or proxying based on the path, you can say. Because now we are talking about that the L7 layer, which is the application layer, and at this level you have all the information of the request. You can see the of course IP address, you have this at the L3 L4 level, but other factors like the path of the complete URL you get here, and all the things which are present in the request. And based on it, it can has its own set of policies configured, and based on that, we as we discussed, like it can, based on the route and the targets, it can define what is the target, right? So it can tell you which microservice we should route to. But of course that microservice is also distributed, so there will be many servers, multiple servers in that microservice. So in order to reach to a particular server in the microservice, we again need a load balancer. So let me write here the L7 load balancer. Okay, Again, the use case of the load balancer is that it needs to pick a particular server now, because there are many servers in that particular microservice where we want to do the forwarding or the proxying or routing, right? So we need to pick a particular server so that one of the servers doesn't get overloaded, because if you put a lot of load on particular server, it will crash, right? So say for example you have 10 servers in a microservice. What you want is like the load is distributed kind of equally to all, or based on other factors also you want it to be distributed. You don't want like one of the servers is getting all the 10 requests, because it will get overload and it will crash. You don't want that kind of setup. So that's why load balancer is there. It will basically assign the request to particular server. Okay, again it can use many techniques, like round robin is there, as we discussed earlier. There is also hashing, but mostly we use at this layer consistent hashing. We will talk about consistent hashing in a separate video, but you can remember that for now L7 load balancer generally uses consistent hashing as a technique to pick a particular server, right? And after this, of course, you have your microservice. So if we are talking about a particular server here, so you can mention it like the server. Okay, we have reached to the server layer now. Okay, so here is the server, and of course further you can also have your database, right? The DB layer which is connected to the server. So let me write it down here, database, right? So the server is connected to the database, but this is your overall, you can say, the flow. The client will interact with this network layer first, and then it goes through all the components like this. Of course these are not kind of mandatory, based on your what kind of system is this. You can skip few of these, but when we talk about like the distributed system, like the big systems, we generally most of the times always have the gateway and the load balancer. So if we are talking in terms of interview, like you are talking about one of the questions, say you are designing Twitter or Instagram or whatever, what you can always do is like in the beginning you will always have the client. Okay, and then you can generally put the gateway here. Okay, the gateway, you can simply tell it will perform the things like authentication using the JWT token, then the rate limiting checks, and then routing the request, right? And then of course you have the load balancer, but you may also skip that. You can simply tell using the load balancer you do that. If you draw it, that's also fine, but further you can basically tell the services. So you can also, when generally in the interviews, you can also skip this part. You can simply say using the load balancer, it will distribute, but it will route to basically different microservices, and then you basically tell this is the microservice which does this part, this is a microservice which does this part, and these are connected to DB, all such kind of things, right? But this is your in detail overall architecture of, you can say, how the API works. So I tried to make it fully detailed so that you get clarity of all the components: DNS, TCP, TLS, firewall, L3 gateway, L4 load balancer, L7 gateway, L7 load balancer. Oh gosh, so much things that we covered in this video. So I tried my best so that you get clarity on the fundamentals and the basics of system design. Believe me, if you understand the basics, makes you feel confident. You feel like you know the stuff, and then basically you can of course go with the deep learning, what are the components that will be involved at higher level for a particular kind of system. Like YouTube will have its own kind of microservices, what kind of database and entities that you will have, message queues, all that stuff will be specific to the system requirement, but these are kind of the basics which will be required in each of the systems. So if you understand this, it makes your life really nice and simple. And believe me, even after working with a long time on the, even on the backend services and stuff, many people might not be clear with these fundamentals. So if you understand these fundamentals, kudos, you'll be at like feeling a wonderful kind of level of confidence. Yeah, so I tried my best to cover everything in this. Please make sure to subscribe to the channel, because that would inspire me to create more such content for you folks. So in case you have any other doubts, feel free to put that in the comment section. I'll try to help you out. So like this video, share it with your friends, so that all of us can learn and grow together. All right, then, this is Mohit Chabda signing off. If you want to know about any other topic, put that in the comment section. I'll see you in the next video. Take care and make sure you subscribe. Okay, bye.